Tell me when you're... Okay, everybody, welcome to this morning session. So we start today with Irene Valenzuela, who's going to talk about the CFT distance conjecture and non-critical strings. So please.
No, I did it. Okay, good. First thing in the morning. So, well, thank you very much. Thank you to the organizers for putting together the conference and the invitation to speak. And thank you to everyone here for waking up early and being the first talk after the conference dinner. Especially thank you to all of you that came also at 9:30 because didn't check the schedule like me. I sympathize. That's even more motivation. So very much appreciated. Okay, so to start the session today, I'm going to tell you about the status of the distance conjecture in CFTs and how it gets related to the appearance of non-critical strings. So this is based, well, it started with this paper years ago with Eric, Leonardo, and Comron, but I want to tell you about recent progress and with José Calderón Infante and ongoing new results regarding these non-critical strings that we are working on right now. Okay, so to start, let me very quickly, or well, not so quickly, review what is the distance conjecture in the Swampland program. So first in the gravitational context before moving to CFTs. So the idea is that if you have an effective field theory weakly coupled to Einstein gravity with a bunch of scalar fields like appears here, the vacuum expectation value of these scalar fields parameterize what is known the moduli space, okay, the scalar field space of the theory. And when these EFTs arise from string theory, there is a very typical feature that we learn, which is that different regions of the moduli space are described by different perturbative descriptions of the theory, which are related by dualities. Okay, it's one of the first things we learn in string theory. And this implies that when we move to different regions, the degrees of freedom that are light and become fundamental are different. And this happens in a very particular way. Okay, so we can quantify a bit better what it means moving in the moduli space by defining a distance. So there is a very natural metric in the moduli space, which is just given by the field metric of the kinetic term of the scalars. And then you can define geodesic distance using this metric, so that whenever we go deeper in the perturbative regimes, which happen to be at infinite distance, using this definition, there are new degrees of freedom that become light, and this happens in a particular way in the sense that the mass of these degrees of freedom becomes light exponentially in terms of this distance. Okay, so if you have, I don't know, some example like type 2b on a circle, you have at large radius, you have the Kaluza-Klein tower of states becoming light, so that tells you that the theory actually contains extra dimensions. But if you go to small radius, you have winding modes now becoming light, and we know that there is a dual description, so they behave as Kaluza-Klein modes in type 2a, so that's the new perturbative description that takes over in that region of the moduli space. Okay, and this always happens in this way. So the distance conjecture is just promoting this feature to a universal constraint and saying that whenever you go to infinite distance in the moduli space, you should always find an infinite tower of states becoming exponentially light in Planck units when approaching any of these infinite distance boundaries. Okay? Good. So this is interesting because it gives us information about when and how Einstein gravity breaks down. Okay, so whenever we find these towers like string modes, Kaluza-Klein modes, I mean, the QFT we had is not valid anymore, right? So it gives you information about the quantum gravity completion that takes over and what is the nature of that theory, like whether it contains strings or extra dimensions or what's going on. So that can have also phenomenological implications. So the distance conjecture plays a central role in the swampland program because it's related to many other constraints. So if you want to start proving this swampland conjecture, this is a good starting point because it has many implications, like many ramifications, and also phenomenological implications. So that's why there has been many works in the past year testing this in the context of string compactifications to Minkowski space, okay, where we have supersymmetric moduli spaces and we can control what's going on in different corners. And there are many things I could tell you about this, like there are many interesting patterns, relations we have found, but the important one for this talk, one of the lessons we extracted by doing this, is that the exponential decay rate, so we say that the mass always becomes exponentially in terms of the distance. So this exponential rate originally was like some random order 1 parameter. It's not random anymore. Okay, so this exponential rate is very constrained, and it depends on the microscopic nature of the tower. So from string compactifications to flat space, we found that so far it seems it always satisfies these bounds, which are saturated either by the critical string, oscillator modes of the critical string, or a Kaluza-Klein tower of the compactifying one dimension. Okay, so I would argue that this is one, if not the most universal feature that we observe in string compactifications. But the question is, can we really prove that it's a universal feature of quantum gravity, or is it just based on the examples that we have? No? How can we try to understand why this is happening, or if it's always going to happen, or just depends on the classes of compactification that we are used to work with? No? Like, okay, we know it works in Calabi-Yau compactification, toroidal compactifications, but it's very difficult to get a proof this way, right? Because we don't have an exhaustive classification of the string landscape. So how we know that we are not missing something, right? So what I want to talk about today is, okay, this is difficult to do, but in the context of ADS, like if we now consider ADS backgrounds, we can translate this feature to a statement on the CFT, and then try to prove it universally. And not just based on examples. Okay, so try to use CFT techniques to prove or disprove this statement as a universal constraint of quantum gravity in ADS. So I thought it fits for this audience because here could imagine that many of you are more familiar with holography than different Calabi-Yau compactifications. For me, it's the other way around, so I'm also now exploring this new landscape. But we'll see that we are actually going to learn new things about CFTs. So let's translate it. So the point is, this moduli space I was talking about, no, the scalar field space, gets translated on the CFT to the conformal manifold, so the space of exactly marginal couplings. And the notion of distance, no, this field that comes from this field metric of the kinetic term, just gets translated to the Samolnikov distance, which is measured by the metric coming from the 2-point function of the marginal operators. Okay. So if you translate this distance conjecture to CFTs, it implies that when you have some local unitary CFT, because I still want to have some gravitational dual, with a conformal manifold, then there should be an infinite tower of primary operators saturating the unitarity bound. That will be the equivalent of saying that they become light in the bulk. At every infinite distance limit, measured by the Samolnikov metric, in such a way that the anomalous dimension of these operators, which is the difference between the scaling dimension and the unitarity bound, scales exponentially, decreases exponentially in terms of this Samolnikov distance. Okay? So this is the statement. I wait a bit so you can think about it. So we should have an infinite tower of operators saturating unitarity bound at every infinite distance limit. And now you can try to see whether it's always realized or not. So, well, we formulated this in this paper for dimension bigger than 2 for the CFT, but similar ideas actually had already appeared in 2 dimensions in these previous papers. And okay, so let's try to do something with this now. So what do we gain by considering now the distance conjecture in area CFT? Well, there are 2 things. First, as I was saying, we can try to prove the swampland distance conjecture using CFT techniques in general. For this, ideally, we would like to show a one-to-one correspondence between the infinite distance limits in the Samorgikov distance and the existence of this infinite tower of operators saturating the unitarity bound. So since we formulated this a few years ago, there have also actually been already 2 papers proving one of these directions in complete generality, like not based on examples, just using the CFTs local and unitary. So this was first paper by Floran and Jose in dimension bigger than 2 CFTs without even assuming supersymmetry. That they saw that when the higher spin gap goes to 0, that's at infinite distance. And more recently by Hiroshi and Jifan for the case of the scalar gap in 2 dimensions. So that direction is already proven and it's left, so the other direction, it's the most tricky one, is not proven yet. It's supported by all the examples, all known CFTs that we have. And we are working on that, okay? So now there are different people trying to think on this direction, and if you know me, I'm an optimistic person, so I really hope we will be able to report on this at some point and really have a proof of this, but we'll see. So that's the status right now. The message I want to give, I'm not gonna talk more about this, but the message I want you to keep also is that it was at least surprising to me that this seems to work in all examples. When I say all examples, I mean any CFT, local and unitary. I'm not requiring that it's a holographic CFT, even, that in the sense that has a large N and large gap. So it even works, I mean, even if this distance conjecture started as a constraint for Einstein gravity theories that we observe in string compactifications, it seems to work even if the gravitational dual is non-Einstein. So it really suggests that it's some universal feature of quantum gravity in ADS. But okay, we'll see. We still have to prove this part. Okay, so the second thing that we gain by translating this to ADS CFT is that, I mean, not only we can use CFT techniques to learn about swampland, but sometimes we can also use swampland insights to learn about CFTs. So in the rest of this talk, what I want to do is actually follow this path in the sense that we are going to start a classification of infinite distance limits in 4D conformal manifolds to see what are the, in practice, what are the towers of operators that we obtain, what do they correspond to, and this will lead us to some classification of the possible tensionless string limits that you can have in these conformal manifolds. So in the gravitational dual implies that some string becomes tensionless, and sometimes we'll see that they correspond to the critical string or more exotic non-critical string backgrounds. Okay. So the question is, yeah, which free strings we can have? No, what is the quantum gravity completions that we have in general for CFTs? Okay, so before starting with this classification, let me make some comments about what is the expected nature of the tower of operators or of states. So let me distinguish between the flat space case and ADS. So in the case of flat space, all these works checking the distance conjecture in different compactifications show that in practice, the tower in the end, it always corresponds in some appropriate dual frame to a Kaluza-Klein tower or oscillator modes of the critical string. This is more constraining than it looks because in string theory you have many different types of objects, okay? And many times when you go to the infinite distance limit, you get, I don't know, like some wrapping brane, some cycles that are the lightest tower. But the whole point is that whenever that happens, you can always find some duality frame in which these wrapping branes behave either as a Kaluza-Klein tower, and that's it, like the D0 branes are Kaluza-Klein tower of M theory, or as the critical string, like if I have an NS5 brane wrapping some 4th cycle, depending on the nature of this 4th cycle, then that actually corresponds to the critical heterotic string. Okay, so these are the possibilities, which tells you that in these cases, yeah, it's always the quantum gravity completion, it's always like a string theory, or and includes extra dimensions. Now, what happens in ADS, okay, from the perspective of the CFT? So here it seems different, the situation, depending on whether I am in 2 or 4 dimensions for the CFT. So in the case of 2 dimensions, it's about scalar operators, the story. In 4 dimensions, seems to be about higher spin operators. You could ask, okay, what about other dimensions? So the point is that dimension bigger than 4, we only have isolated CFTs. We don't have conformal manifolds. And in dimension equals 3, the examples are typically compact. Okay, so if we want to consider infinite distance limits, then the CFTs that we know that have infinite distance limits are 4-dimensional. And there's still the question of whether one can show that 3D are always compact or not. Okay, so in this talk, I'm going to focus actually on D equals 4, okay? And the question is, okay, I'm gonna show how these higher spin operators appear, and we are gonna try to understand what do they correspond to in the bulk. Is it always the critical string as happen in flat space, or can we get more exotic things? Sorry, this is the same. Yeah, okay, so let's focus on 4D CFTs. So with any level of supersymmetry. So now I want to take this landscape of CFTs, like known CFTs, and study what are the possibilities. So the infinite distance limits that are known in these cases, they always correspond to weak coupling limits, in the sense that there is a gauge coupling of the CFT gauge theory that goes to 0. And so there is a subsector of the CFT that becomes free. Now it's easy to see why these free limits are at infinite distance, because, well, these are complex conformal manifolds. So the gauge coupling is part of this complex marginal coupling. And when we are at weak coupling, the marginal operator is just trace of F squared. So we can compute the 2-point function to obtain the Samorgikov metric. And just because this is the perturbative limit, it always takes this hyperbolic behavior, so that when you compute the distance using this metric, you find that the weak coupling limit is at infinite distance in the conformal manifold. Okay? Good. Now, the point is that when we have a free sector, it was shown by Mandelstam and Sivoedov that that's equivalent to having a higher spin symmetry, in the sense that we have infinitely many a continuum of higher spin operators saturating the unitarity bound. So you have the conserved higher spin currents. So you can see what's going on now. So whenever we have these weak coupling limits, they are at infinite distance, but also they have these higher spin operators that saturate the unitarity bound. And moreover, one can show, just because this is a perturbative regime, that the anomalous dimension goes as the gauge coupling square. So in terms of the distance, indeed behaves exponentially with the Samorgikov distance. So the CFT distance conjecture is realized in all these cases. And not only is realized, but we can be very quantitative about how the mass, well, anomalous dimension here goes to 0. What are the exponential rates? So, for example, if we think that we have some large n CFT, we can translate this to the mass of some states in the bulk. And then when writing the mass in Planck units, just to relate to the usual distance conjecture, then the exponential rate goes as the square root of 2 times the central charge of the theory over the dimension of the gauge group that gets free. And that's universal for any of these weak coupling limits. Okay. So first observation is that indeed this has a lower bound, because the dimension of the gauge group cannot be larger than the central charge. So there's a lower bound on how light the states become, which give you an upper bound on the cutoff of the theory. So you know that at the very least, you should find states at a given scale. So that's interesting. Okay, so yes. So here we are moving the conformal manifold of a CFT, so for fixed central charge. So it's the total, like, okay, you mean which central charge? Yeah, C and A. So I'm talking about C, like for, okay. A will appear later. Good. No, the free theory, it's in the strict limit. This is like when approaching the limit, so it's becoming free, but it's not exactly free yet. It's perturbative, it's like a perturbative gauge theory. The value of C? No, because I'm moving the conformal manifold, so C is fixed. Yeah, exactly. Okay. Yeah, yes, it's the same, just mean it's the same data at the free point, any points, yeah. Okay, good. Okay, so this is the general result for the exponential rate. So what do the higher spin states correspond to in the bulk? So let me just first show it in the canonical example, right, of n equals 4 super mean. So here, of course, when the gauge coupling goes to 0, what's going on is that we are sending GS in the bulk to 0, right? And then what happens is that indeed the fundamental string is becoming tensionless in Planck units, right? Because the ratio between the string scale and the Planck scale is controlled by GS. So this weak coupling limit of the CFT indeed corresponds to a tensionless limit of the type 2B string in the bulk. And the higher spin tower of operators map to the oscillator modes of the critical string. Okay. Good. So the exponential rate you can compute it for n equals 4 super means is 1 over square root of 2. And just one side comment. You can ask me about this later if you are interested, but just want to remark that it's important to keep in mind that this result is valid in the perturbative regime of the CFT. So this is small TOF coupling. It can be connected to the supergravity result that we would obtain at large TOF coupling. And we actually do this carefully in the paper with Jose using integrability results. And there's a very nice connection between the two as you change the value of the TOF coupling in such a way that the bounds I showed you at the beginning coming from the Swampland are satisfied. And in a spin-off, we can also use this to give some argument for ideal scale separation, but that would be a different topic, so ask me about this later if you're interested. Because you change n. Here what you are doing is to change what is the rate. So n goes to infinity, the gauge coupling goes to 0, but they can go with different rates. Like the ratio is different depending on the value of the TOF coupling. And the point is that when you go to large, so the quantization of the string is different if you are in the background in which the curvatures are very large, or you are in the background in which you are the perturbative regime of the CFT, so the curvature is for the radius. So this is, okay, this is the alpha, so this would need more time to explain, so I can show you later. This is the alpha in the conformal manifold. Okay, this would be like the alpha taking into account both directions. So it depends which limit, which trajectory we are taking. So it becomes more like path, depends on the path. But you can follow for any path and see how it changes depending on which path you take. Here would be only moving the conformal manifold, here we're moving in a different trajectory, but I can show you later. Okay, so just wanted to say, so n equals 4 super mil is clear that this limit is the tensionless string limit of the critical string, but what about other for the CFTs? Okay, so what are the possible values of the exponential rate, and what does the higher spin tower correspond to? Okay, is it always the critical string, or can we get other things? So to start, let me see. Okay, to start the classification, in these papers, we restrict our attention first to 4 DCFTs with large n, because I'm interested in understanding the bulk dual, even if it's not Einstein, but it's still at least having some gravitational weakly coupled theory. And we restrict the attention to gauge theories that have a simple factor. So I only have one gauge coupling. It's just to simplify my life. It's not the whole thing, but it's the first starting point to start considering more general cases with several gauge coupling and different type of limits. Okay. So if you restrict to this case, there is actually a full classification of the possible CFTs you can have with a simple gauge factor. So we are going to the weak coupling, so that's why in this limit they become Lagrangian, right? Because the gauge coupling is going to 0. And this is the possible theories you have with the values of the central charges and so on. This is written in n=1 language, but here you have both n=1 and n=2 theories. The point is that I divided all these theories in 3 tables, which correspond to the 3 values that you get for alpha in this landscape of CFTs. Okay, so in other words, you take all CFTs, 40 CFTs with large n and a simple factor of the gauge group, and you only obtain these 3 possible values of the exponential rate for the higher spin tower. And as you see, it doesn't depend on what is the gauge group. Here you have SUN, USP, and SON, and so on. And it doesn't depend on whether it's n=1 or n=2. It's like different thing, okay? So you might wonder, okay, what's special, right, about these 3 classes? What distinguishes them, right? Why we have these 3 values? What do they correspond to? So in this case, since we only have one gauge factor, okay, we can write this exponential rate purely in terms of the central charges of the CFT, so both A and C. And this happens to be, the alpha depends only on the ratio between A and C. So these 3 values happen because for this landscape, for this mini landscape of CFTs, it happens that there are only 3 values for the ratio of A over C. The first one is precisely the holographic CFTs, right? So A is equal C. So this will be dual to Einstein theories. And this is indeed the value that we have in n=4 super Mills that corresponds to the critical type 2B string. So the first class is just, this higher spin tower will just correspond to oscillator modes of the critical string in all these Einstein theories. So in other words, all Einstein theories that have A = C have the same higher spin tower, which is just the critical string. Okay. What about the others? Okay. These are not holographic in the sense that even if I have a large n limit, A is different from C, so there will be higher derivative corrections that are not suppressed because typically you don't have a large gap. Okay. So what are these higher spin states? Okay. So the Swampland insight is that from checking this in many compactifications, as I said, we learned that the value of alpha give us information about the microscopic nature of the tower. So this suggests that these 3 values correspond to 3 different towers of oscillator string modes. Okay, so 3 different types of tensionless string limits. So we can kind of classify all the CFTs in categories depending on what is the tensionless string limit that we have. So what is the dual string background? And the goal is to check, okay, whether this is indeed the case, whether they correspond to string and what is that string. No? So how much time I have? It's 28. Okay, 5 minutes. Okay, good. So we did 2 things. First, we compute the thermal partition function, the 3 sphere at the free limit for all these CFTs. So including any content of matter, any value of the gauge group, to show that indeed they all exhibit a Hagedorn-like density of states. But indeed, when we compute the Hagedorn temperature, it's different for each of these 3 classes. And then we give some universal result for the Hagedorn temperature that depends purely on the value of alpha, or equivalently in the value of the ratio between A and C. So that we have a different Hagedorn temperature for each of these 3 types of CFTs. So this suggests that indeed they correspond to some stringy-like object. But we want to do more, okay? We want to understand whether we can infer what is this object in the bulk. So As I said, the first one is just the critical string, but the other ones, they take place in non-Einstein theory, so are difficult to analyze from the bulk. But something we can do, and with this I will finish the talk, is that we can construct some interpolating models that, starting from some holographic CFT that we know what is the bulk dual, we can take some limit and obtain these other non-holographic ones and follow the limits to see what this string corresponds to. Okay? So this is an idea that we actually borrow from this paper, for example, of Gary Bowman and Rastelli, which they did this for this particular theory, which is n equals 2 super QCD. And what we are doing is to do this for all the others. Okay, so very quickly here I had like some summary of what they did in this particular example, because it's a canonical example. Maybe I will go quickly because I don't want to run out of time. So in this paper, they can show that n equals 2 super QCD. You can construct it from an interpolating model, starting from SUN cross SUN, taking one of the gauge couplings to 0 while the other is fixed. So that decouples, and what is left is this n equals 2 super QCD. So if you know the brain picture and the gravity dual on this side, now you can follow this limit here and see what you get here. Okay, what is the dual? So may skip this. The point is that you can, in this case, you have DC brains on an A1 singularity, so you can dualize this to have this elliptic model in which you have two NS5 brains and D4 brains between them. And this limit here, this weak coupling limit, corresponds to a double scaling limit in which you approach the two NS5 at the same time that GS goes to 0, such that the ratio between the two gets fixed. Okay, so that's equivalent to sending only one of the gauge couplings to 0. And therefore, what is left would be like some stack of D3 and D5 brains in a non-critical strip background, in the sense that has less dimensions. This is the Worset CFT before taking into account the back reaction of the brains. And then the gravitational dual is like this back-reacted subcritical background that, well, Andrea and collaborators, Leonardo, they have studied more detail in this recent paper. Okay, so only have 7 geometric dimensions. So this is the last slide. So the point is that we construct interpolating models for all the other theories. And indeed, we saw that all these ones that have the same value of alpha, they all come from approaching two NS5 brains with different content of the open string sector. Okay, but then the weak coupling limit we are talking about would be like the tensionless limit of this non-critical string background. And the others, they come from approaching 3 NS5 brains. That's what distinguishes them, with different content of the brains and orientifers. And therefore, this weak coupling limit with this other value of the exponential rate corresponds to the tensionless limit of this other string background. And these are just, so it's for me surprising that you start with this full classification purely from CFT, and you just get that they just come like the closed string background, they are dual. It just comes from this simple stack, no, the system of approaching these NS5 brains, and that's it. Okay, so let me flash the conclusion. So the distance conjecture seems to be some universal property of conformal manifolds, even beyond Einstein. We started some classification of the infinite distance limit corresponding to these tensionless string limits of critical and non-critical backgrounds. In this case, there are only 3, which now we can understand where they came from. And of course, you can imagine the next step is to go beyond this mini landscape and start considering more than one gauge factor. So thank you for your attention.
You mentioned that these operators saturate the unitarity bound,
yeah.
But from your examples, these are operators, in fact, that are marginal. Why do you use this?
No, the marginal, so you have the marginal operators for the conformal manifold, but then you have higher spin operators that the anomalous dimension depends on the marginal coupling.
I agree, but what I'm
Yeah.
trying to say, if you take a scalar, when it becomes massless in the bulk, eventually it's a boundary marginal operator, not an operator of dimension 1, which is the unitarity bound. That's why I'm confused.
But here are higher spin operators, not the scalar operators.
Some like trace F square are scalars.
Yes, but the operator, so these are different. So it depends. There are several operators involved in this game, no? So of course you have these ones, but then you have higher spin operators just constructed from, taking derivative, right, of the scalars and so on. And then the anomalous dimension depends on the gauge coupling square. And these are the ones that saturate the unitarity bound as the gauge coupling goes to 0. Yeah.
So there is no scalar operator in there.
Here, not exactly. So in 2 dimensions, it's different. Okay, it's 2 dimensions.
In string theory, there are scalar operators, right? When you take these decoupling limits, when the scalars.
You also, so it's different. So you also have, but it's not the ones that become exponential on the distance.
Scalar Kaluza-Klein states.
Yes, but that's the point. So in flat space, we have Kaluza-Klein states. Here in 4D CFTs, it seems that what we always find are not Kaluza-Klein states, but only these higher spin operators. So they are always like weak coupling string limits.
Thank you.
Yeah.
Hi, I have a naive question. Why does it stop at 3 NS5 brains?
Why does it stop at
Why
3? Okay, that's not a naive question. So yeah, when I give you this, like the natural question is, okay, what about if I collide 4 or 5 or 6 or 7, right? The point is that right now I started from the CFT, so I considered theories that only have 1 gauge factor, right? If I have more than 3 NS5 brains, what I'm gonna get when approaching the brains are gonna be CFTs that have more than 1 gauge factor. So right now, yeah, exactly. So my understanding is that this was kind of an artifact of having only 1 gauge factor. And now when we extend the classification to having more than 1 gauge coupling, we are gonna find, yeah, like 3 up to infinity, no, NS5 brains. And the question is, do we only find that, or we will also find something different?
Thank you.
So I guess one natural question is why you're only looking at gauge couplings. I don't know, other interesting.
So the point is that the only known examples of infinite distance limits in 4D CFTs, or like CFTs dimension bigger than 2, correspond to weak coupling limits, that the gauge coupling goes to 0. So here I was trying to do a classification of things that are known, like the landscape of CFTs we know. So that's why I restrict to those ones. But then the question is, okay, can you show that this is the only possibility, no? Or could it be that there is a different infinite distance limit that is not a gauge coupling going to 0? And that's what is left to show, to prove that CFT distance conjecture. Like if one can prove, for instance, that this is the only way to go to infinite distance, to have a weak coupling limit, then we would complete the proof of the conjecture, because then we know what happens in that case, and that's it. There is nothing else. So part of the, when we are trying to prove the conjecture, what we are trying to understand is whether this is the only option or there are other options, no? How to show this and what happens then. But so far there is no example, so it's like, yeah.
And you can also maybe go some intermediate step, right? And say, okay, it's a gauge coupling. So what kind of imprint does this have on the spectrum of higher spin states? And can I show at least that this property is always true rather than directly proving that it's a gauge coupling?
Yeah,
but are there some obvious imprints, or is that hard to see? Like, I guess, do you have only even spins, higher spin currents, something? I don't know. I'm just guessing.
Well, you have the spin 4, you have all of them. It's not, so far we have only studied how the anomalous dimension behaves. You can try to go more details, no? About the trajectory, the radio trajectory. Maybe there is a way to do it. I think...
For example, spin 4, but not spin 3, something like that.
yeah, in all these cases, I mean, you have all the spins in the end. Like you have the, no, spin 3 might depend on the case. Yeah, spin 4 or more. Yeah. I'm sure there are more things that can be done. Something that it's more clear is that if it's free, if you have a free sector, for instance, we can show that this free sector necessarily is about a free vector multiple. Like it's really about a gauge coupling going to 0 if we have a superconformal free theory. That we can show in general. So if it's free, that's it. So the question is it always at infinite distance, do we always get something free? Or can we have something different?
Yes. Yes. Okay. That'd be great. Yeah.
Okay. Now we have next speaker, Martin Sasieto, is going to talk about ER for typical EPR.
Okay. Thank you very much to everyone for coming, and thanks for the invitation. Also, thanks to the organizers for putting up this really nice conference here. I'm really having a great time. So today I'm going to change topics a little bit from what Irene has told us, and I will essentially talk about black holes. Okay. Okay, so everything that I'm going to say today is going to be based on these two papers that came out earlier this year in collaboration with Javier Magan, who's at the Instituto Balseiro in Argentina, and with Brian Swingle, who is at Brandeis. Okay. Okay. So let me start by giving you a broad motivation to why we are interested in this kind of problem. So in ADS-CFT and in general in holography, there are two ideas that have appeared over the last decade or so, which appear to be in tension. Okay, one is famously known as ER equals EPR, and I'm sure like all of you have heard about this slogan before. Essentially, the idea is that enough microscopic entanglement between two holographic quantum systems generates some notion of an emergent space. Okay. So this is, of course, best understood for quantum systems that describe black holes, in which case if you start with two black holes which are entangled, they're entangled enough, what emerges, the space that emerges is essentially the black hole interior. Okay. So the classic example in holography to try to understand this is to place two holographic systems here on the left, on the right, on this specific quantum state, quantum pure state, okay, which is entangled. So this state is called the thermophile double state, and it is a very special entangled state in that it canonically purifies the thermal state on one of the two systems. So this state contains a large number of EPR pairs, so it contains a large number a large amount of entanglement. And the point is that this state is semi-classically dual to the eternal black hole in ADS. So more precisely, what this means is that the semi-classical dual to this microscopic state lives on some Cauchy slice of this bulk geometry. The point is that this Cauchy slice is connected between the two ADS asymptotic boundaries. So the spatial connectivity of the semi-classical dual to this state essentially comes from the amount of entanglement of this state. Okay, that's sort of the general idea. So the second idea, which appears to be in tension with this one, is that the thermophile double example or other situations, which are sort of simple, they are very fine-tuned, and they are not generic examples of entangled states between two black holes. So in particular, there's been arguments over the past saying that perhaps a generic entangled state of the two black holes doesn't have an interior, and it perhaps contains some non-perturbative object that you can call a firewall or something else that nobody knows how to describe. So as you see, this kind of idea is sort of against the mantra of ER equals EPR. So the question we want to try to understand is whether more generic entangled states of two black holes have semi-classical interiors or not. Okay, whether generic EPRs of two black holes have ERs associated to them. Okay, so let me, in order to define what I mean by typical or generic entangled state, let me start by illustrating the definition in the simplest case, which is a collection of n qubits at infinite temperature. So if we just take two such systems, so we took two collections of n qubits, and just consider maximally entangled states, we will generate some collection of states, which I'm here referring to as EPR. Okay? So this is essentially a set within the Hilbert space of the two systems of qubits. It's a subset of states. And the infinite temperature thermofield double is one such state. So in particular, the infinite temperature thermofield double has this particular wave function in the energy basis. So you see that it's diagonal. These i's are the energy eigenstates of some Hamiltonian. And one property is that the wave function is diagonal, and it, moreover, doesn't contain any phases. Okay. So this is a canonical purification of a thermal state in the sense that if you compute the reduced density matrix to one of the two systems of qubits, you get a maximally mixed state, which is the infinite temperature Gibbs state. Okay. So a typical EPR is essentially a generic point in this set. So the thermofield double is not very non-generic. Okay. So in order to define generic, you need to specify some measure. And the natural measure that is sort of inherited from the natural measure in the space of unitaries is essentially the Haar measure. Okay? So essentially the point is that a typical EPR can be constructed by applying some random unitary to one of the two systems in the infinite temperature thermofield double. And this will land us in a generic point in this set. So if you diagonalize the wave function of a typical EPR, it looks pretty much like the infinite temperature thermofield double, but now you get a collection of phases, and moreover, the eigenvectors are different from the energy eigenstates. They are other vectors that essentially correspond to the eigenvectors of the unitary that you use to create the state. So a typical EPR can equivalently be defined by a statistical distribution of phases and a statistical distribution of eigenvectors. Okay? In particular, for a typical EPR, the eigenvectors are uniform random states in Hilbert space, and the eigenphases are distributed in a very particular way. They are distributed according to the circular unitary ensemble, which is a famous ensemble in random matrix theory. Okay? So for us, the important property is that if you just focus on the wave function of a typical EPR, the nearby eigenphases tend to statistically repel each other. And one can see this empirically just by taking some high dimension unitary and plotting the eigenphases of this unitary on the unit circle. And with this information, one can make a histogram of the eigenphase separation between the nearby eigenphases. And you see, statistically, nearby eigenphases are correlated in such a way that it's very unlikely for them to be close to each other. So in this sense, they repel each other. So this is a defining property of the CUE. And as you see, the infinite temperature thermofield double is very atypical because all of the eigenphases are essentially zero. Okay, so the argument by Marov and Polchinski was essentially that typical EPRs, like this state that I wrote here, they have the same entanglement as the infinite temperature thermofield double, in that if you compute the reduced density matrix to one of the two sides, it gives you an infinite temperature density matrix. However, if you want to compute a correlation function between left and right system in a typical EPR for a simple operator, say a local operator, the value of this correlation function is typically exponentially small in the entropy of the system, and moreover, it very erratically depends on the specific microstate that you chose, the specific phases of the wave function and eigenvectors of the typical EPR. And so this signal is very erratic and exponentially small, and therefore they argued that this was enough to conclude that it cannot be reproduced semi-classically. Okay? So there must be something very quantum gravitational for a typical EPR of two black holes. That was the sort of argument. So in this talk, I will try to argue that this is not the case by very explicitly constructing families of Einstein-Rosen bridges, so black hole interiors, which incorporate this erraticity semi-classically, which provide a window into the generic structure of the Hilbert space of two black holes in any theory which contains gravity and matter in the low energy sector. Okay? So these wormholes are essentially very long. They are characterized by some total length L, and they are supported by a large number of matter inhomogeneities. Okay? And essentially, the other length scale which characterizes the wormhole is the scale of matter inhomogeneities, which is this L delta. And we call these wormholes caterpillars for obvious reasons. Okay? And in the second part of my talk, I will show that the microstates dual to these kind of semi-classical states are actually very close to being typical EPRs of the two black holes. So I will quantify, using the gravitational path integral, a correspondence between a microscopic measure of how random the states look and the semi-classical, I will relate this notion to a semi-classical properties of the geometry, like the length of the wormhole. Okay? So in some sense, I will derive a correspondence between quantum randomness, holographic quantum randomness, and the emergence of the length of the wormhole in the black hole interior. Okay, so the goal is to start from the thermofield level, because the thermofield level is a state that we understand very well in holography, and from there try to build a generic entangled state of two black holes. The natural thing to do is to just take the thermofield level and time evolve it with some time-independent Hamiltonian. Okay? So this will produce a trajectory in this space of maximally entangled states, in this example, in this qubit example. And essentially, we will end up with some time-dependent state whose wave function looks like this. So the basis which diagonalizes the wave function is essentially the energy eigenbasis of the Hamiltonian. And now it will acquire a bunch of phases. So this will make it more generic. And these phases will essentially be given by they will be characterized by the energy eigenstates, okay? By the energy eigenvalues. So it is, It is easy to see that this state will never become typical. The reason is that this trajectory that we are evolving our state with doesn't explore a generic point in Hilbert space. So essentially, the conservation of energy along the trajectory, the conservation of the Hamiltonian, prevents the trajectory from exploring most of the Hilbert space. So it only explores a measure zero subset of the space of maximally entangled states, and therefore this state never becomes a typical EPR. Okay. A way to see this is, well, it's pretty simple. One can just focus on the energy eigenvectors. If our Hamiltonian is a few-body Hamiltonian, this means that it only contains few-body interactions. The energy eigenstates are not random states, and therefore, as I told you before, a typical EPR has a random state diagonal form. So this state will never become a typical EPR, already for few-body Hamiltonians. But even if we consider completely non-local Hamiltonians, or random matrix, then these vectors are uniform random states, but these phases will fail to incorporate the characteristic eigenphase repulsion of the eigenphases of a random unitary. Okay? And a way to see this is just, well, empirically, you can just take some time evolution operator at very, very long times for some random matrix here, plot the eigenphases. So here I'm plotting them at timescales comparable to the inverse mean level spacing. This means at timescales which are exponential in the entropy of the system. And you see that the difference is that the eigenphases tend to clamp on top of each other. So the eigenphase separation in this case is given, the histogram is given by a Poisson distribution. Okay? So this shows that the eigenphase repulsion is absent in this kind of state. Nevertheless, this kind of strategy to time evolve a thermofield double has been used in the past to try to explore the the Hilbert space of black holes. And the idea is that if you time evolve the thermophile double, so the thermophile double lives, the semi-classical dual lives in this t equals 0 slice. If you time evolve it forwards, then essentially what happens is that the wormhole in the black hole interior grows in time. Okay? So this already tells us that a more generic wormhole is a longer wormhole than the one for the thermophile double. Okay? This can be also understood from the fact that the thermophile double has very large correlations between the two systems. So it is a KMS state. Okay, and there's been ideas, following this logic, which relate notions associated to the time evolution, like its complexity and so on, to the geometric growing of the length in the black hole interior. And essentially the idea is that the length of the wormhole is related to some notion of complexity of time evolution, although nobody has been able to make this very precise. Okay. So, but my point here is that even at exponentially long times, as I showed you before, the state becomes sort of very, very complex. It's very difficult to generate it from a thermophile double. However, it doesn't become typical. And perhaps one way to see this semi-classically is that the wormhole becomes exponentially long, but it is still given by a vacuum solution to Einstein's equation. So a vacuum solution is sort of, which is also very symmetric, cannot be generic. Okay. Nevertheless, there's been a lot of recent work to try to understand this regime of exponential times where some quantum gravity effects are supposed to take over. Okay. So what we did was to instead consider the evolution by time-dependent Hamiltonians. Okay, so our time evolution is now some time order exponential of some time-dependent Hamiltonian. And specifically, it will be convenient to choose a specific class of time-dependent Hamiltonians, which are called Brownian Hamiltonians. These Hamiltonians consist of a few, of a set of operators, which I will think of them as few body. So in holographic systems, this would be like single trace operators. Okay, and next to each operator, we choose some time-dependent coupling, and we sum over operators. Okay, this is the generic form of the Hamiltonian. And essentially what makes it Brownian is that we are choosing the time-dependent couplings from a white noise correlated Gaussian random distribution. So our each coupling is chosen at random at each time step with zero mean, with a variance which is independent at different times. So essentially the couplings are uncorrelated at different times, and the variance is controlled by some scale J that we define here. Okay. And the intuitive picture is that this time evolution, this class of time evolution, it will generate some sort of Brownian motion in the space of maximally entangled state when we apply it to the infinite temperature thermophile double. So this Brownian motion will eventually be able to explore the whole Hilbert space and generate a typical entangled state. And yeah, the Brownian Hamiltonians, they are sort of known in quantum chaos and quantum information literature because they provide a continuous version of what is known as a random quantum circuit, which is essentially a discrete time evolution, discrete time model where is a model of quantum computation where the gates at each time step are chosen randomly. So here what we are doing is choosing the Hamiltonian randomly at each time step, which is a continuous version of that. Okay, so let me just tell you what the advantage of choosing this kind of dynamics is. The advantage is essentially that we can solve the dynamics on average exactly. And let me just illustrate this with what is known as the spectral form factor. I could do it with correlation functions as well, but let's just, for simplicity, consider the spectral form factor, which is some correlation function of the spectrum of the time evolution operator. Okay? So the spectral form factor is defined as trace of u of t squared and then average over couplings. The idea is that for Brownian Hamiltonians, one can write this down as an effective thermal partition function with some effective Hamiltonian, which is also known as the Liouvillean in quantum Markov processes. Okay, so the idea is that the correlations between couplings on different contours, so trace of u of t squared, each contour prepares trace of u of t, and there's random couplings on each contour. The average over couplings produces effective interactions between contours in the form of a time-independent effective Hamiltonian. The effective Hamiltonian contains quadratic interactions between the operators on both contours. Okay. So essentially, computing some very complicated quantity on average reduces to a sort of simple quantum StatMech problem. Another interesting property which makes this sort of solvable at very late times for a generic set of operators is that the ground state of this effective Hamiltonian is known. It is the infinite temperature thermofield double. And if the operators are generic enough, we expect the Hamiltonian to be gapped. We expect this ground state to be unique. And so we can, at very late times, this kind of quantity will be dominated. So T is just the inverse temperature. Late times is like low temperatures. This kind of partition function will be dominated by the ground state, which gives a 1 contribution. Then it will be dominated, the leading correction will come from the first excited states. So there's n star number of first excited states generally, and they have some energy E gap here. Okay. So we've computed the spectral form factor in a very generic way for any Brownian Hamiltonian. So this kind of form is very universal. Let's now compare it to what is expected for the spectral form factor for time evolution operators generated by time-independent Hamiltonians. So this is what is famously known as the slope, ramp, and plateau structures in the spectral form factor, okay, which essentially represent the fact that the Hamiltonian is chaotic, in particular the ramp is what represents the fact that the Hamiltonian is chaotic. But what I want to show here is that when we computed this value of 1 for the spectral form factor is essentially, what's going on? Is essentially, the value of 1 is essentially this very late time value. And we can compare this very late time value with the very late time value for the spectral form factor for a time independent Hamiltonian. And as you see, they are very far apart from each other. Particularly, they are exponentially far apart from each other. So this is essentially a manifestation of the fact that the Brownian evolution is able to generate the correlations of a random unitary, whereas the time-independent Hamiltonians are not able to generate that. Okay, so this value of the plateau essentially comes from the eigenphase repulsion that I was talking about before. Okay, so this is sort of generic. Let's try to apply this time evolution to holographic systems describing black holes. So the first problem we encounter is that, well, Brownian Hamiltonians, they are just time-dependent couplings. They will inject energy into the system. And so a black hole in ADS-CFT is a thermal state at finite temperature. So if we just naively apply the time evolution operator to a thermofield double, we'll end up with some time-evolved thermofield double with a bunch of matter shocks inserted into the black hole. So essentially, here I'm thinking about the operators that drive the Brownian evolution as local single trace primaries of the CFT. And so the semi-classical duals of those operators are just bulk matter fields, like supergravity fields in top-down examples. And so this will essentially inject a bunch of matter into the black hole, and the black hole will grow, and we will eventually lose track of the original black hole that we started with. So that's not ideal. Essentially, this is a continuous time version of what it was considered by Schenker and Stanford to study scrambling in black holes. Okay, but the point is that if we just do that for the time evolution operator driven by some time-dependent couplings, there will be a maximum time after which the back reaction will become very strong, and we will lose track of the black hole. This time scale is of the order of the entropy of the black hole divided by the number of perturbations. Okay. So we want to keep track of a equilibrium black hole for timescales which are much parametrically longer than that in principle. Okay, so the idea is essentially to time evolve the black hole with this Brownian time evolution infinitesimally, and then cool the state down with some Euclidean evolution. And do this sort of infinitesimally over and over again. And in this way, generate some finite temperature version of this Brownian evolution. So we will take the infinitesimal time steps of Euclidean and Lorentzian evolution to 0 while keeping t fixed. Okay. Formally, this operator can be written as some, path integral in the CFT along some complex time contour, which looks like this. Okay, it doesn't matter really what it looks like for this talk, but the point is that even though these time faults might look a little bit exotic, they are there to implement the interaction Hamiltonian where only the Brownian time evolution is important, and the bare Hamiltonian of the black hole is sort of not contributing to this kind of evolution. And what we will do is to prepare states of two CFTs just by performing the CFT path integral along this complex time contour. Okay, so this will prepare some state at time t for a single realization of the couplings. And given that we are considering random couplings, we will have an ensemble of states at fixed time t. Okay, so in holography, to try to understand the semi-classical dual, the holographic dual to a given microstate, what we typically do is to use the ADS-CFT dictionary, which tells us that we should compute the norm of the state at a Hartle-Hawking, and then evaluate the norm of the state using the gravitational path integral in the bulk with the boundary conditions given by the actual CFT data that we use to create the state. Okay. So of course, doing this for a single realization of the couplings for Brownian evolution is very, very hard because this is a time-dependent problem. In general, the bulk solution will not be real, and it's very complicated to consider the back reaction of matter and so on here. So a trick that you can use in order to elucidate coarse-grained properties over the ensemble is just to take the average over the couplings. And again, the Brownian dynamics simplifies matters because the average value of the norm can be written as some time-independent quantity, in particular as the survival amplitude of the thermophile double state, time evolved with a Euclidean time-independent Hamiltonian by a time t. Okay, so this is sort of like more complicated version of the spectral form factor sort of simplification that I was telling you about before. Okay. In this case, this is a finite temperature effective Hamiltonian, so it's different than the infinite temperature one. And one can show that it has this form. So it has the previous form with quadratic interactions coming from the correlations between couplings correlated between replicas here. And then it has these additional terms coming from the fact that we're cooling the system down gradually. So these terms appear from the cooling. This class of Hamiltonians has been studied in ADS-CFT in the context of making wormholes traversable. Okay, so essentially, if there's a large number of perturbations, one can sort of very generically argue, if the Hamiltonian is chaotic, that this effective Hamiltonian contains a unique ground state, which looks pretty much like the thermophile double. And so time evolving with this Hamiltonian on this particular state does nothing. And so this thermophile double looking state semi-classically should be a connected spatial wormhole. And so the full space-time should be that of a traversable wormhole if we decide to evolve with this Hamiltonian. Okay. The point is that this Hamiltonian contains interactions between the two boundaries, and so the wormhole becomes traversable because of that. But for our purposes, we just want to compute this thing, this norm, this average norm, gravitationally using the gravitational path integral. Okay. We can do this very explicitly in low-dimensional models. So for instance, if we just think about the SYK model, where all of the states are states in the product of two SYK systems, we can write down, we can use the fact that this effective Hamiltonian has been studied in this context by Maldacena and Chi, to write down this norm as some effective classical problem for some, classical particle mechanics for some specific variable, which is L. So essentially, this is another formulation of JT gravity, which is related to the one that Samir reviewed in his talk. And the idea is that this L parameterizes the geodesic length between different boundaries. Okay, and it is a gauge invariant variable. So there's some SL2R gauge symmetry there, and this length is the gauge invariant variable that you should use when you have two boundaries. And so essentially the problem, JT gravity reduces to the particle mechanics of a Liouville wall. So it's an exponential potential. And so what happens is that this effective interaction, in this case, has been studied and introduces some other term. Okay. And so one can solve for this disk geometry very explicitly in that case. What happens essentially is that this additional term stabilizes the length between the two boundaries. And so the disk stretches for that reason. So essentially, the length is stabilized and there is some effective, some approximate time translation symmetry of the solution. And so the disk gets stretched. Okay. So the point is that one can, okay, we've computed, we want to compute the norm of the state. So this is the bra. Sorry, the bra is in the top half. The ket is in the bottom half. We're averaging over couplings. We're solving for the gravitational saddle point. So the semi-classical dual essentially lives on the time symmetric slice of this saddle point. And it turns out that for the reason that this length variable is stabilized and there is some time translation symmetry of the geometry, one can show that the analytic continuation of this space-time looks like a two-sided black hole with a very long black hole interior, okay? So the length of the wormhole is essentially proportional to the circuit time that we use to prepare states, using the fact that this approximate isometry appears in the calculation. Okay, and one can argue that the same thing happens in higher dimensions using generic properties of the effective Hamiltonian, although in that case the calculation is much more complicated. And yeah, we didn't do it in higher dimensions. But the point is that this shows that the length of the ensemble of caterpillars is on average growing linearly with the circuit time that we use to prepare the states. If we want to just compute the slopes, we can essentially use the fact that the effective Hamiltonian is gapped in SYK JT gravity. This can be computed explicitly. Essentially, the first excited states are fermion excitations on the wormhole. And what happens is that one can use this information to measure length locally in units of the matter correlation scale. So this scale is essentially the scale of decay of the two-point function for a matter operator, for the lightest matter operator on the wormhole. And this E gap is essentially the boundary energy times energy scale. So this relates the bulk quantities, length in units of this matter correlation scale, to the boundary quantities, which is the boundary time used to prepare the state in units of the gap of the effective Hamiltonian. Okay. So this is the geometry part of the talk. We'll now try to relate this length to some microscopic property of the ensemble of states. So the idea is that, as I told you before, if you just time evolve the thermophile double with the Brownian evolution, it will become more and more generic. So it will become more and more random, more and more typical. And one can quantify how random a state or an ensemble of states becomes in terms of the quantum information notion of a quantum state K design. So the idea is that a K design is an ensemble of states which reproduces the first K moments of the random state ensemble. So for K equals 1, that means that any expectation value that you take on this ensemble is on average given by the same value as the expectation value of the ensemble of typical EPR states. So in particular, this means that if you have a 1 design, the ensemble appears thermalized on average. So any state that you pick from this ensemble, which is sort of generic within the ensemble, will have equilibrated expectation values, given that the random states have equilibrated expectation values for any operator. So K equals 2 is a much stronger requirement. It just means that K equals 1 is true. So all the expectation values are given by the random expectation values. But moreover, the variances of the expectation values are also given by the random ensemble, as well as nonlinear quantities over states, which are quadratic. Like, for instance, the second Renyi entropy of the reduced density matrix to one of the two sides. Okay. So physically, this is a very strong requirement, even though from the quantum information perspective, this is natural. So already to have a 2 design is something kind of very strong. But yeah, we will try to study how this K of a K design grows in time in gravity. Okay. So at infinite temperature for this Brownian time evolution, one can show that very generally, very universally, this K grows linearly in time. Okay, so the ensemble of states that one creates using this Brownian motion becomes more and more random in a very quantitative way. So the amount of randomness grows linearly in time for that case. So the question is what happens in gravity. Okay. So in order to do this, to try to compute K for black holes, we need to essentially compute the distance to a K design. And this is given in terms of some quantum information quantity, which is known as the frame potential of the ensemble of states. Essentially, the idea is that one needs to compute the overlap between two independent states of this ensemble to the power of 2K, and then take the average over the couplings. And this quantity is just a number that depends on time. It's just a function of time. When this number is close to the infinite time value, then the ensemble is very close to a K design. Okay? So for K equals 1, we just need to compute the square of the average between two independent states of the ensemble. So this is just two replicas, each of which computes some overlap. We need to take the average of this thing over the couplings. And again, because of the Brownian couplings, the problem reduces to computing a quantum stat-mech partition function for some effective Hamiltonian coupling the two K replicas together. So this is a more complicated version of the things that I was talking about before, but one can sort of write down this quantity as some quantum stat-mech partition function at inverse temperature 2T. And the idea is that this effective Hamiltonian, at very long times, this quantum stat-mech partition function will be dominated by the ground space and the first excitations. So very generally, one can show that, well, essentially what happens is that the low energy sector of this effective Hamiltonian breaks replica symmetry and is dominated by K copies of the two replica effective Hamiltonian. So essentially, the whole problem in 2K replicas reduces to an effective problem in two replicas. Okay. So in gravity, this is yes, thank you. This is manifested from the fact that we can compute this kind of thing gravitationally using the gravitational path integral, and the dominant contribution at late times comes from a two-boundary wormhole. Okay, so one can compute the frame potentials for holographic systems using the gravitational path integral, get an expression at late times that looks like this. So essentially, the frame potential is the infinite value, which counts the number of ground states times 1 plus the first excitations of the two replica effective Hamiltonian and some exponentially decaying function of time. And this allows us to compute the distance of the ensemble of states to a K design and show that it decreases exponentially in time. And essentially, the number of ground states scales exponentially with K because there's this K factorial. And so one can impose that eventually at some time Tk, the distance is smaller than epsilon, and so the ensemble of states becomes an approximate K design, and show from this kind of formula that K for gravity grows linearly in time with the slope given by the gap of the two replica effective Hamiltonian. So this is a sort of very general argument, but it works in gravity because of this two replica wormhole, which can be explicitly constructed. Okay. So what we showed here is that randomness grows linearly with the same slope as the average length of the wormhole. So combining both linear growths, we get our main result, which is that the ensemble of caterpillars of length L and matter correlation scale L delta forms an approximate quantum state K design of the black hole for a K which grows linearly in L over L delta. Okay, so let me just emphasize this. This relation is a relation between some microscopic property of the ensemble of microstates, which is this K, which is the randomness that they have, so how random they look. And on the right-hand side, we have a quantity which is purely semi-classical. It's just the length of the wormhole. And so this constitutes a complexity geometry relation in holography, but which has been derived from first principles using the gravitational path integral. So this linear growth of K has been computed. Okay? So let me just end with general remarks and with some discussion. So the ensemble of caterpillars that we constructed, we show that they provide a window into the generic structure of the Hilbert space of black holes in any gravitational theory which contains matter. Okay, any gravitationally theory which contains matter, you can construct these states. And in principle, if this theory can be non-perturbatively completed to some holographic theory, these states are supposed to be generic states in that Hilbert space. So there's many open questions from our constructions. One of them is whether the caterpillar states contain firewalls or not. So because there's been this discussion in the literature of whether typical states of black holes contain firewalls. So firewalls in this case, they would correspond to very highly boosted matter shocks, which are hugging the black hole horizon and which collide with the black hole, so collide with the infalling observer once the infalling observer crosses the horizon. So it's not clear whether these caterpillars, which are just, the slices of the space-time, when you evolve them, they develop these kind of firewalls. In particular, there's been recent claims in the literature or proposals saying that half of the typical states should contain firewalls. So there should be half of the caterpillars in principle which contain firewalls. Okay. There's also the issue of reproducing signals explicitly, like the signal of the left-right correlation function for some operator. That's non-trivial of whether the caterpillar saddle point is the dominant saddle point in that case. So it would be nice to get this kind of analysis done. Another interesting problem is whether we can form K-designs of black holes in other ways than just adding matter in the black hole interior. And this relates to the ways that people in quantum information generate K-designs, which could include performing measurements or LOCCs. In particular, this relates in holography to the ideas in these papers by Malacena Kurkulu and by Jan de Boer and friends, where they, they start from some thermofield double state, they do some measurement on one of the two systems, and they end up with some more generic state with some end-of-the-world brane in the interior. So this kind of thing could also serve to form K-designs. It would be interesting to study the relation between the two kind of states. Okay, and let me just end with some very generic comment. So the matter that forms the caterpillar eventually falls into a singularity. So we've characterized more generic black hole microstates in terms of their semi-classical geometry. This would be telling us that the singularities that these states have are also more generic from the microscopic point of view. So it will be interesting to relate this genericity between the microstates to the genericity of the singularities in the form of some BKL kind of analysis. Okay? So this is all that I wanted to say. Thank you very much for your attention.
Hi, thanks for the very clear talk. There's one point which is not clear to me. Why do you call these things semi-classical? If I understood correctly, you have to average over the Schwarzian to get the results in what you call the geometric picture.
Right. The point is that these couplings are semi-classical. So
yeah, but the calculation is in the quantum gravitational theory, right? Okay.
Yeah, it's just that we're doing saddle point approximation to every quantity after averaging over couplings. We're just taking the leading saddle point, and that's.
No, I mean in the bulk. You're using the. You have to do this calculation of Malacena and friends that you have to average over the. You have to calculate a quantum expectation value in the Schwarzian theory.
Right. Yeah.
So the early time behavior of the spectral form factor typically shows a random matrix universality, which is a smooth power law decay. But the plot you showed had some sort of oscillation in the slope region. Could you perhaps
well, that depends on the ensemble, right? Like for GUE, you get this. Do you mean like the black line?
Yeah. That's sort of the oscillations that you have.
This is some Bessel function that you get from GUE, like for the average density of states. If you Fourier transform that.
I see. Yeah, typically it's like 1 over t cube from the Wigner semicircle or near the edge.
Yes, you're right.
But here probably it's because of the specific ensemble that you were considering.
Yes, you're right.
Okay,
thank you.
Thank you very much.
So you showed this linear growth of the wormhole, And let's believe that it's related to the complexity of the boundary state. So from qualitative arguments with system of qubits, it's understood that at very late time it should saturate to a certain point, but very late, so exponential in the entropy. So I was wondering whether you see something like that, or you have an argument in your description for this thing to happen?
Yeah, that's a good question. No, we cannot access that regime like within our semi-classical sort of, we're using the gravitational path integral within the disk approximation. We're not doing anything non-perturbative or anything like that. So yeah, it would be interesting to see whether randomness saturates as complexity. Yeah.
Okay, then thank the speaker again. And now there is the coffee break and we reconvene at 11:50. No.
Thank you.
What is this?
And this is based on work with my very nice collaborators. So Jelle Harting in Edinburgh, his PhD student Vijay and Melly, and Gerben Oling, who is in the audience. So feel free to ask both me and him if you have anything that is unclear during the talk. Very good. So just to set the stage, wait, let's see. There we go. I had to press the other one. So all of this takes place within the context of, in some sense, flat space holography. And there is a very nice anecdote from Strings in '98, where Witten sort of muses on this topic. And he says this funny thing that, okay, we want to find a flat space version of the ADS-CFT correspondence. But of course, the boundary in flat space, or asymptotically flat space, is a little bit funny. So he says this funny thing that, okay, a too naive version of structure X, which is this putative dual to gravity in asymptotically flat space-time, is some kind of field theory on null infinity with what he calls the peculiar differential geometry. And as we will see, this peculiar differential geometry is precisely what has now come to be known as Carolian geometry. So just to give you a bit more motivation before we get into the meat of the talk, in the ADS-CFT correspondence, I don't need to tell you, of course, that the energy momentum tensor on the boundary plays a big role. It's sort of the response to varying the metric. And the way that you get this energy momentum tensor is essentially by performing this procedure known as holographic renormalization. And the way that works is essentially that you solve Einstein's equations near the boundary while keeping the metric on the boundary free. And then by varying the on-shell but renormalized action, because generically it diverges, so you need to renormalize it. By varying this renormalized on-shell action, you can extract, by varying this boundary metric, the energy momentum tensor on the boundary, which is then the CFT energy momentum tensor. So the goal of this talk will be to do the same for asymptotically flat spacetimes, namely carry out this holographic renormalization procedure. And rather than having a Lorentzian geometry on the boundary in asymptotically flat spacetimes, we have a conformal Carolian geometry. I'll tell you exactly what that means. So just by analogy, what we must understand is the near boundary on-shell description of gravity as captured by the Einstein-Hilbert action in asymptotically flat spacetimes, and in particular with arbitrary Carolian data at future null infinity. Very good. And please, if you have any questions, interrupt. Doesn't matter if I don't quite get to the end of the talk. Very good. So just to give you a small taste of what this word Carolian means, which we saw it already in Siki's talk, but in case you haven't really heard of this before, it's maybe slightly exotic. One way to think of it is as something you get when you take the speed of light c going to 0, in which case the light cones close up like this. And that has all kinds of peculiar consequences, namely that the screen goes black and there's no light in the Carolian world. Everything. But just to make a long story short, what happens is that exactly the opposite to what would happen in the Galilean limit. So rather than time becoming absolute, which is perhaps more familiar, space becomes absolute when the light cone closes. And what replaces a metric in the geometric version of this is this so-called Carolian structure consisting of what's called the Carolian vector field and a Carolian ruler, which has co-rank 1 with a kernel spanned by this Carolian vector field. And you should think of this H as sort of like a spatial metric in quotation. It's not a metric, but it sort of measures spatial distances. In the context of what we're doing here, you should maybe think of it as some kind of generalized version of the metric on the celestial sphere. If we add sort of conformality to the mix, these structures and their inverses, so tau and h, it's not too important, but together with the v and the h with the indices downstairs, these form a complete set of sort of what corresponds to the metric and its inverse. And they transform in a certain way under Weil rescalings and under these so-called Carroll boosts, which is sort of, they shift this so-called clock form, which is the dual to the Carolian vector field, and there's a v missing here, so this should be 2v mu. So these symmetries will come back to haunt us later. But just to tell you what exactly I will be talking about. So first, I'll just discuss how you actually get this near boundary structure up and running, and how to really see this completely arbitrary Carolian geometry on the boundary, namely on null infinity. Then I'll tell you about how variations work in this framework. It'll turn out there is a certain constraint that the formalism places on the boundary geometry. So you need to deal with constraint variations. And then at the end, I will go through the procedure of holographic renormalization for asymptotically flat spacetimes. And in particular, that will reveal that the shear plays a very important role. So to set up this framework, what we're doing is really just, we consider a box standard Lorentzian metric in an asymptotically flat spacetimes, and we write it in a vielbein decomposition. So this is, this is a very standard thing, except that here, rather than having sort of normal time-like and space-like vielbein, we've combined one time-like and one space-like vielbein into two null vielbein. So this you can always do. And then we treat null infinity, so the boundary here, as a Penrose boundary, and there is this very standard thing that Penrose came up with, which essentially involves the introduction of what's called a defining function, which is basically the radial coordinate that is such that when you take it to infinity, you land on null infinity. And what you do next is you just partially gauge fix the local Lorentz transformation that acts on these vielbeine to get the metric into this form. So these objects will appear quite frequently, but this is just a choice of your local Lorentz transformation. So we don't fix all of it, but we fix them such that we land in this choice. And then this Penrose construction fixes the boundary conditions for the fields that appear in these objects. And precisely what happens, and we will see exactly how this goes, what exactly happens is that when we go to the boundary, these objects essentially give rise to this Carolian structure that I showed you on the previous slide. Of course, they appear at different order in R. So, for example, this the thing that gives rise to this so-called ruler appears at order R squared in the expansion of this pi, which sits here. But this is all dictated by this Penrose construction. So we've already fixed some of the local Lorentz symmetries, but there's much more to fix. We have a lot of fixing to do. But the strategy is really to fix all symmetries that we can, such that the boundary Carolian structure remains completely arbitrary. And this is important precisely because we want to vary it so as to get a response, just like in the ADS-CFT correspondence. Normally, so in order to do that, we fix these Levi-Civita connection components here in this way. And in some sense, this provides a covariant generalization of the Bondi gauge. So that's why we call it, and it's covariant with respect to the Carolian structure. So it's Carol covariant. Of course, what's usually done is that you fix the symmetries further to go to the full Bondi gauge, where the clock form is related to the retarded time. And this metric, the ruler here, just reduces to that on the celestial sphere. Where I remind you that D, again, is this, essentially, so D plus 2 is the dimension of the bulk space-time, so D plus 1 is the boundary, and then, of course, the celestial sphere will have D dimensions. Now, as I mentioned, there is a constraint, and this constraint enters here, so it turns out that Einstein's equations force this so-called, it's related to something called the intrinsic torsion, but this funny extrinsic curvature-looking thing, K mu nu, which is the lead derivative along the ruler, along the Carolian vector field of the ruler, is constrained to be pure trace. So this is a constraint only when D is greater than 2. So in particular, it is a constraint for 4 bulk space-time dimensions. But we will see how to deal with that later. Now, if we solve Einstein's equations order by order in R, what we find is the following. So the expansion looks like this. So at leading order, we already knew from the Penrose construction, we get the Carolian ruler. At the next to leading order, we get this C, which is the shear. So it's symmetric and trace-free and spatial, which means that if we contract it with V, the Carolian vector field, we get 0. This S is quite important. So remember, S was really the GRR up. So it's going to be related to the norm of the normal of a constant R hypersurface. So that's going to be important when we consider holographic renormalization and cut off constant R hypersurfaces. but we'll get there. The last thing on this slide is just an explicit identification of the residual transformations with the Carolian symmetries I showed you on the first slide. So the residual diffeomorphisms look like this, where in particular the radial component of these guys become the Weyl transformations I showed you on the previous slide. The subleading boundary diffeos become Carol boosts, parameterized by this lambda. And then these leading guys just become boundary diffeos, the parameter of boundary diffeos. And so these two we already saw, but this guy, the shear, which of course is a very important object because it sort of, if you were considering scattering problems, that is sort of the thing that captures graviton scattering. But here it's just a funny object that transforms in a certain way. So it has a derivative on the boost parameter, suggesting a connection with, some kind of Carol boost connection. I will not go into it. I will just mention that this covariant derivative is a particular choice of covariant derivative for the Carolian geometry. The details are not so important. You can make any choice you like in a sense, as long as the full thing behaves nicely. So you can endow this with certain properties, but ask me later if you're interested in how that works. Very good. So if you then, in a bit more detail, solve this thing, what you find is that the metric, the near boundary expansion on shell looks like this, where you see the shear sitting in this component. And then you see in this component that you have, well, here I have abbreviated things a little bit, but these guys are all essentially defined in terms of geometric data that comes from things like, curvatures and things defined in terms of tau and h. But there is some structure that is not determined by Einstein's equations, and that precisely will go into the definition of the energy momentum tensor, and we will see how that happens. So just to give you a little bit of an idea of how these variations work, if you take an action functional depending on the Carolian structure and the shear, its variation looks like this. So it will turn out that the shear is on par with the Carolian structure, so that the variation takes this form. And together, these three responses define what's called an energy momentum tensor news complex, so the energy momentum tensor plus the news. And by varying these guys under the symmetries of this action, so which we assume are there, they turn out to not be quite there, but if we assume they are there, we get certain void identities corresponding to diffeomorphisms, Weyl rescalings, and Carol boosts. So they will come back to haunt us as well. But now, for the holographic renormalization, what you need is essentially a well-posed variational principle. So if you just take the Einstein-Hilbert action and you vary it, you find that it's a boundary term, so there's an x missing here. But it takes this form in 4 bulk space-time dimensions. And the standard thing is that you need some kind of Gibbons-Hogg-Yawking boundary term to make the variational principle well-posed. But here, this S guy that I mentioned comes back to bite us, because if you do this on a constant R hypersurface, you find that this hypersurface doesn't have a definite signature. So it's not null, it's not space-like, it can be anything. Luckily, roughly 10 years ago, these gentlemen came up with a counter term that precisely deals with this issue, and it takes this form. And when we then add this, the variation takes this particular form. This part we like, it looks like what we had in the other slide, but this part we don't like because this precisely contains variations of free data. So we cancel that by just adding this term that removes this variation. And this in the context of ADS-CFT would be like a cosmological constant term. But, so that we add, but that introduces additional divergences that we then must get rid of. And it turns out that we can get rid of these by adding this term, where C is now some well-chosen connection on these constant R hypersurfaces. In addition to that, we can introduce improvements via finite counter terms that endow these responses with certain properties that we like. So once we do that, add a suitable intrinsic counter term, which is reasonably complicated, but it can be done. It looks annoying, so I don't write it. But once you do it, you find that the full variation, as you go to the boundary, takes this form. And what is a little bit special, and what you should really appreciate here, is that this funny term here appears. So you see, it's not here a priori, but it really appears for two reasons. So this curly T, which is sort of the finite version of the T, is order r to the -3, plus the fact that if you take S with delta H, that is a total derivative. And these two facts combined give rise to this structure and really is what pushes up the shear to be on par with the Carolian structure. So that is something quite special that happens as a consequence of this holographic renormalization procedure. And then you can see, okay, suppose that this action was actually invariant under all the symmetries. We'd have these void identities that I showed you on the previous slide. And then you just say, okay, you can explicitly compute these guys from this procedure. Do they satisfy these void identities? And it turns out that they satisfy the Weil void identity, but not the boost void identity. There is a boost anomaly. So this anomaly is Wess-Sumino consistent, and it just sits here. So the boosts are anomalous. Very good. So the diffie void identity turns into a covariant version of the Bondi loss equations. They look like this. I'm just flashing it here to say that there's an explicit result that reduces to known results when you sort of gauge fix further. And this n, in case you're wondering, is sort of a Weil invariant version of the News tensor. So usually the News is just the retarded time derivative of the shear. And this is, if you take v to be like minus du, this is roughly that, and k to be 0. So to end, let me just give you, so of course this opens up many, many interesting new directions of future research. So one burning question is, of course, does there exist some kind of analog of n equals 4 super Yang mills on the boundary that we can somehow write down? Is there really a dual field theory that does this? Is there some kind of Carolian boundary CFT? We don't quite know, I would say. Of course, since we're at Eurostrings, it would be extremely interesting to connect this with other very interesting works that actually explicitly embed a simplified version of this into sort of topological B models, where you can consider a stack of D1 branes and get a very interesting version of this for something called Burn space. So that would be interesting is to see if there's some connection with this. And then more generally, just to connect this to this whole celestial program, where instead of considering the dual to live on this null infinity, you really consider the dual field theory to live on the celestial sphere over which null infinity fibers. So yeah, thanks a lot for your attention.
Questions? Yeah.
Regarding the Carroll boost invariance, so in your boundary action, you were varying the field that you call ruler, so H with lower indices.
Yes.
But also the clock one form and
Yes.
not the vector field.
Yes.
Can you comment why you used clock one form and not the vector field?
Yeah, so the thing about that is, so that is a choice. You could also vary it's just because the way that the energy momentum tensor is, so the response to varying the clock is the energy current. And that's sort of more convenient to vary with respect to than, so you could have also used the Carolian vector field, that would be equivalent.
But the clock one form is not Carroll boost invariant.
No,
the vector field is.
No,
right?
Exactly. And what that means is just that you get the boost void identity will involve the energy current, right? So you write T mu delta tau mu, and then you transform the tau mu under a boost, and that then will tell you if you were in a pure Carolian theory that the spatial projection of the energy current is 0.
Okay.
Great. Thanks a lot for the question.
Okay, there are no more questions. Let's thank the speaker again.
Thanks.
Okay, so next speaker is Erika Bertolini, and she's going to talk about quasi-topological mass generation for 3D linearized gravity. Okay.
Thank you. First of all, thanks to the organizers for this very nice conference and for giving me the opportunity to share with all of you one of my latest research. So I've been working on higher engaged theories lately, and this made me investigate a bit more on some aspects of modified gravity and linearized gravity, especially. So why are people interested in massive gravity? So it is known from observation that the universe is in an accelerated expansion, and this was first explained in terms of the cosmological constant giving some kind of negative pressure and interpreted therefore as a dark energy. This thus predicted from observation a certain value of the cosmological constant, but this is in disagreement with some quantum field theoretical predictions. Some other ways for justifying this accelerated expansion can be found, for instance, in the context of FOR's theories. But lately, people have been interested also even more in massive gravity theories, because from developments in the observation of gravitational waves from LIGO and Virgo, for instance, an upper bound, a non-zero upper bound on the mass of the graviton has been defined. That's a very small bound, but it's non-zero, and this gave a push into the investigation of massive gravity theory, which, through the existence of a possible long-range potential, could explain also this accelerated expansion. So that's why massive gravity. So in my talk, I'm going to work on 3 space-time dimensions. So why is it interesting in the context of massive theory? So it has a lot of peculiarities, and it's been used as a toy model for testing new physics in a lot of context, and especially also in some massive gravity theory, as I will show you in a few slides. And that's because in 3 space-time dimension, gravity is renormalizable, which is the consequence of being a topological theory, and therefore it has no local degrees of freedom, no propagating massless gravitons, and therefore no gravitational waves in the massless case. But some surprising things appear with the massive introduction. But so how do one see that there is no gravitational wave? So the linearized gravity action in 3 space-time dimension is the usual one, doesn't change in any way. It's still invariant under diffeomorphism. And so by considering the customary covariant gauge, the harmonic gauge, one can find through the equations of motion, again, the usual wave equation, so nothing changes here. However, in the further studying this on the TT gauge, one can see that this gives enough constraints to completely switch off, let's say, the gauge field. So then this means that the theory has no propagating degrees of freedom in this case. But this will change when a massive term is introduced. And this has been done at least twice in the past. So there are 2 main models for gravity, for massive gravity in 3 dimensions. And the first one was developed in 1982 by Deza, Jakiv, and Templeton, and it's called topological massive gravity. And the second one was developed in 2009 by Berkshire, Forman, and Townsend, and it's known as new massive gravities. So in the first case, it is described by the following action term. So the standard, more or less, Einstein-Hilbert term is coupled to a higher derivative term, which is the following one. So I'm saying more or less because there is actually a minus sign in front of the Einstein-Hilbert term. That's relevant, and it's necessary to get positive energy states. And this higher derivative term as a massive coefficient with negative dimension And it's parity violating and generates mass through Maxwell-Chern Simons-like topological mass generation, which was actually described in the same paper. By computing the linearized equations, one can see that the Klein-Gordon equation for the D'Alembertian of the gauge field in the TT gauge gives a mass for the graviton. And the number of degrees of freedom can be identified by decomposing the gauge field, as I will show you in a few slides. And this shows that this model is describing 1 degree of freedom, one massive degree of freedom related to the transverse part of the gauge field, and it's a spin 2. On the other hand, the new massive gravity model is similar. So we have, again, the Einstein-Hilbert term with negative sign and a higher derivative term in terms of the Ricci tensor and scalar. This time, the theory is parity preserving, and the mass generation mechanism is more like a Fierz-Pauli term, let's say. We can compare the two. One is written in terms of the just metric perturbation, the other with Ricci tensor, but they look alike a bit. And in the same way as the Fierz-Pauli term is tuned in order to avoid ghost-like states, this 3/8 factor is there for the same purpose, so in order to avoid ghost states. And here again, the mass appears as in the Klein-Gordon equation for the Einstein tensor. This additional equation is the one responsible for removing the ghost-like part. So this model instead describes 2 propagating degrees of massive degrees of freedom of spin 2 and mass μn. So the 2 models share some similarities and some differences. For instance, in the topological massive gravity case, this exists only in 3 space-time dimensions. That's because it's of the presence of the Levy-Civitas tensor, while new massive gravity a priori exists in any dimension, even though I think there are some issues in the higher dimensions. The first one is parity violating, and the other one is parity preserving. And this is is connected to the fact that one has 1 degree of freedom, massive degree of freedom, and the other 2. But there are also some other open, let's say, aspects, open questions that are related to the fact that the massive part has a coefficient with negative mass dimensions, which then implies that the massless limit is actually reached only for the mass going to infinity, which actually gives not just the pure, let's say, usual Einstein-Hilbert term, but the same with a minus sign, which was said to be wrong sign in the new massive gravity paper. Also, it's in some sense in disagreement with the physical situation, because the mass of the graviton, as I show you at the beginning, it's actually very tiny. So we should get the linearized gravity term for a very small mass, so for mu going to 0 instead of infinite. And these are actually effective theories, since we can build infinite invariant terms. So this last open points, let's say, motivated the work with my collaborators that was actually recently published. And so I have to underline that a difference here is that we are going to work only on the linearized gravity part. So the nonlinear version will be studied in the future. On the contrary, in the topological massive gravity and new massive gravity, they started from the nonlinear terms. So we started with some requirements for the theory. So we want to have a well-defined massless limit that gives us the linearized gravity term with proper sign. We want propagators to be well-defined in the massless limit and to have massive poles. and no physical ghosts should appear in the theory. This has to be compatible with power counting, and the degrees of freedom, the massive degrees of freedom should be related to the spin 2 components, since we want a theory of massive gravity. And this should be in agreement with one of the two models that I've been describing, because we don't want to have a huge plethora of very different theory ones. We want some agreements. So that was the proposal. So we have our action that's composed of the linearized gravity term plus a massive contribution. And the massive contribution is given by this Chen-Simons-like term. So it is linear in the derivative. It's not topological because we have summation over the indices. And the whole theory is actually not invariant under the complete set of diffeomorphism symmetry, but only under a subset of it, which is called longitudinal diffeomorphism. A side comment, this symmetry is related to a class of theories known as covariant fraction theory, which I've been working for some time as well. So just that side, we can already see that this model satisfies two of the requirements. So it has a good massless limit, which gives us the linearized gravity term with proper sign, and it's compatible with power counting. So now we want to go on. We want to treat this as a gauge theory. And therefore, since our gauge transformation has a scalar gauge parameter, we impose a scalar gauge fixing. We do this by introducing this gauge fixing term to the total action. And now we compute the propagator and see if we have also the other points being satisfied. So sadly, it turns out that this doesn't work. So some of the coefficient has a pole on the mass. So this propagator doesn't have any good massless limit. But not all hopes are lost, because actually we should have treated this as a usual gauge theory, a massive one, where the mass breaks the gauge invariance, and our real symmetry is related to the diffeomorphism. So we want to consider the theory with a vector gauge fixing, so the usual harmonic one with the following gauge fixing term, therefore. One interesting thing is that the symmetry is broken by the mass term, but actually it is broken in a controlled way, because we can see that its variation on the gauge fixing actually vanishes. And this is an interesting sign, because it's telling us that there is probably a hidden symmetry of the whole gauge fixed action, so some kind of PRS symmetry, as I will show you at the end. So now we can go on and study the whole theory with the new gauge fixing term and look at the propagator, which now we're happy we have a good result. And we see that the coefficient of the propagator has a massless limit, a non-divergent massless limit, and it's giving us the propagator of linearized gravity when the mass goes to 0. And it's also telling us that the gauge field has a mass that's related to m, to the mass parameter. Additionally, we can see that there is no physical ghost or tachyonic poles appearing, and we can say something more if we look at the propagators on another basis, which is known as the Barn-Rietvers basis. This has a nice feature of being written in terms of spin projectors for a symmetric rank 2 tensor, which means, in particular, we can look for the poles related to the P2, so the spin 2 part. And that's results. So we see that the massive pole is actually related only to the P2 contribution, which is telling us that the theory has a massive spin 2 degrees of freedom. But we can go on and even counting the degrees of freedom, as I was anticipating at the beginning. One can do this as it was done in the paper by Nezerjikov and Templeton. And so we can decompose the gauge field in terms of irreducible representations of the rotation group, and then further on in terms of transverse, longitudinal, and solenoidal part. This satisfies the following relations. And then we can therefore look at the action in terms of this decomposition. And we see that some multipliers appear that we can integrate out, and they gives us some constraint for our theory, which gives us in the end the following action term. So this depends on only one scalar, and there is and the equations of motion are telling us that this is the one related to the Klein-Gordon equation, to the massive Klein-Gordon equation. So the massive propagating degree of freedom is 1, and it is this box of U. But what is this physically? So we can do the same decomposition on the Ricci tensor, for instance, and see that in the harmonic gauge, which is the one we are considering and the one that restore the breaking of the gauge symmetry, we see that this box of U, the D'Alembertian, is related to the transverse part of the spatial Ricci tensor. Therefore, it is the transverse part of the spatial Ricci tensor which is related to the massive Klein-Gordon equation, which is again in agreement with the result of Nezerjikov and Templeton for the topological massive gravity. Finally, we can, as a proper gauge fixing procedure, one needs to consider the BRS transformation, as I was mentioning. And so we need to introduce some ghost and anti-ghost fields and their transformation. And we still have the usual diffeomorphism transformation in terms of the ghost field. And this is a symmetry of the gauge fixed action, of the massless gauge fixed action. But it is broken by the massive contribution, but then by the massive term. However, we've seen that there is a controlled symmetry breaking. I mentioned that that was a sign of a new symmetry, and in fact, we can define a new modified BRS-like operator through this additional term, and this is indeed a symmetry of the whole massive gauge fixed action. And not just this, because this new BRS operator is not nilpotent anymore. However, we are exchanging this nilpotency with the existence of a new operator delta, which is again a symmetry of the action. And it gives us a new algebraic structure for the theory, which is actually similar to a known one for topological Schwartz-like field theories. And this is another reason why we're calling this model quasi-topological. But what's important here is that we have a symmetry related to this Ward operators that is uniquely identifying this our theory. So I can just summarize here that we finally had a three-dimensional massive model that satisfied the requirements. So it has a good massless limits. It's giving us the linearized gravity term with proper sign. The propagators is well defined with the good gauge fixing term. There is no unphysical ghost appearing. It's power counting compatible, and the degrees of freedom, the degree of freedom, which is 1, is massive, and it's related to the spin 2 component of the gauge field. But not just this, we also got an additional surprising result. So we found that there is a BRS-like symmetry, a BRS-like structure that's uniquely identifying this theory. So what to do next? Well, first of all, we want to identify the nonlinear theory, so to connect to the, let's say, logical structure of the other models. This then would help us to get to the four-dimensional extension, if there exists one, and how it looks like, and further investigating the the new extended symmetry, which could give us some hints for the four-dimensional extension, for instance. And I wanted to thank you all.
Questions? Can you make some comments about that? Thank you.
Well, I could give a whole talk about this, but yeah, I don't have the time. Yeah, it's just interesting because, yeah, so fractals are related to this. So
I asked because at some point in the talk, she mentioned about the connection with fractals, and I asked if she could comment a bit more on that.
So yeah, fractals appears as a gauge theory invariant under this symmetry. So one can define a full set of actions that are typically Maxwell-like, but refer to higher ranks gauge fields, typically ranked to symmetric gauge fields. And so yeah, linearized gravity can be considered as a particular case of it, which is additionally invariant under the diffeomorphism symmetry. But so fractals are quasi-particles, so are more related to the condensed matter side, and they describe quasi-particle with limited mobility and some kind of Maxwell-like structure, therefore higher rank gauge fields. So and this action term is also related, can be studied on its own, like a Chern-Simons-like term, and this on its own can be associated to some covariant fractal theories. So it seems like there is some intertwine there that's relating linearized gravity and these models. But yeah, this would require a long talk. Thanks for the question.
Thanks.
So if you consider a Wilbein formulation with Lorentz connection and 3-bind, there's a natural term which you can write, which is just product of epsilon E omega, which would be nonlinear. I'm not sure, maybe it vanishes, but it looks like nonlinear generalization of this term, which will have.
Yeah, that's another aspect that we were thinking of studying in the future. I was talking to a collaborator about this recently. Yeah. Yeah, that's
okay. Let's see other questions. Okay, then we can thank the speakers again.
A minute, sorry. Yeah. You give me a sign, yeah?
Okay, so the next and last speaker of the morning session is Franz Cherry, and he's going to talk about towards holography for the IKKT matrix model.
Yeah. Yeah, so hi everyone. First of all, let me thank the organizer for this nice conference and for giving me the opportunity to present my recent work in collaboration with Henning Zamtleben about this IKKT matrix model. So this model, as the name suggests, is a series of n by n matrices, SUN matrices in 0 space-time dimensions with 16 supersymmetries and SO10 invariants. So the action is given by the following formula and involves 10 bosonic matrices, which I call X here. So the index A runs from 1 to 10, which transforms in the vectorial representation of SO10, and 16 fermionic matrices psi, which transforms in the spinorial representation of SO10. So here I don't write explicitly the spinor index on the matrices. And so this model was originally proposed a long time ago by Ishibashi, Kawai, Kitazawa, and Tsuchiya as a non-perturbative definition of type 2B string theory. And of course, this begs the question of how space-time and gravity can hide and emerge from a series of pure matrices. So in this talk, I would like to take a modern perspective on the question, which relies on the fact that this matrix model actually arises in the context of holographic dualities. And the holographic dualities that are relevant here are the ones that relate strings or supergravity series on the near-horizon geometry of DP branes, which is of the form of an ADS spacetime in p+2 dimension and a sphere factor in 8 - p dimension. And so this side is related to p+1 dimensional super Yang-Mills series with 16 supercharges. So of course, for p is equal to 3, this is the very well-known ADS-CFT correspondence between type 2B strings on ADS5 cross S5 and an equal 4 super Yang-Mills in 4 dimensions. So as you decrease p, the field theory on the boundary of that lives on the boundary of the ADS space becomes more and more minimalistic, but it still conjecture to encode the full string theory on the gravity side. So when you reach the extremal case of p is equal to -1, the field theory living on this 0-dimensional boundary of this 1-dimensional ADS space is actually the IK-KT matrix model, and so this suggests a duality for this IK-KT matrix model. So despite intriguing and highly non-trivial result in this IK-KT model, this duality has remained so far largely unexplored, and I think that this is partially due to the fact that there hasn't been any clear dictionary that has been established between fields in the bulk and operators in the matrix model. And that means also that there has never been really operators that have been identified that can be computed and compared on both sides. So in this talk, I would like to make a very humble step in this direction and argue that the lowest BPS multiplet of single trace operator in the IK-KT matrix model is realized in the bulk as the lowest Kaluza-Klein fluctuation around the 9th sphere of the near-horizon geometry of D-1 brane, and that this lowest Kaluza-Klein fluctuation can be consistently described at the nonlinear level by a one-dimensional supergravity theory. Okay, so if this all sounds kind of mysterious to you right now, it's pretty good because the goal of the talk is to make it more clear. So essentially the plan is to start with the gravity side, and only at the very end I will come back to the matrix model. So the machinery we have that we use on the gravity side is, the notion of a consistent Kaluza-Klein truncation. So let me start by saying some words about this. Oh no. It doesn't appear okay, there are some parts of text that don't appear. But okay, you have another PDF viewer or sometimes. Everybody close their fingers. Okay, so maybe I can continue in the meantime. So what we'll be interested in is, yeah, this is okay, and then, no, okay, it doesn't work, but okay, I'll do it without it. So the relevant Kaluza-Klein truncation for us here are Kaluza-Klein truncation of gravity series on spheres. So it means that what you do is you start from some gravity theory and you expand all your fields on a background which is a sphere. If you do that, you get an infinite number of Kaluza-Klein mode, and when you do truncation, it means that you keep only the lowest Kaluza-Klein mode in this tower. And in particular here, the ones that I want to do are called this Pauli truncation, where these lowest modes include a spin 2, as well as some non-abelian gauge boson for the SOQ plus 1 isometric group of the sphere, and a bunch of scalar fields as well. And so the dynamics of this lowest mode is described by a lower dimensional theory, which is a gravity theory coupled to SOQ plus 1 Young-Mills, and some scalar fields that come with a scalar potential. So the question is whether you can do this truncation consistently, in the sense that the modes that you have kept are not going to source the mode that you have thrown away. It is actually a non-trivial question for the sphere. When you do it on the torus, it's simple, because you keep the 0 mode on the torus, and because they are all singlet under the isometric group of the torus, you know that they will never be able to source non-singlet. But in this case, the modes you keep are not singlet under this SOQ plus 1. I mean, the Young-Mills fields are in the adjoint, and the scalar fields are charged, so the consistency of the truncation is not ensured. So in practice, what you actually have to do is that you have to write a truncation ansatz for your high dimensional field, where essentially for each higher dimensional field, you write it in terms of the lower dimensional field, and the dependence on the sphere coordinate is captured by some kind of geometric quantity like the embedding coordinates of the sphere, or the Killing vectors, or the Killing tensors. And then you have to plug this ansatz into the higher dimensional field equation, and you have to show that the whole coordinate depends on the sphere factorizes out and leaves you with the field equation of the lower dimensional theory. Of course, this is usually very hard to do, because these truncations at Z are very nonlinear, and gravity theories are very nonlinear to start with, so it's difficult to prove. And in fact, what we know is that this does not work for pure gravity. If you start for pure gravity in D dimension, you cannot do such sphere truncations. And so the only way for these sphere truncations to work is if you start from some matter-coupled gravity theories with specific matter content and specific couplings. And it turns out that the cases when it works, I mean, these are typically the couplings that appear in supergravity. So here I'll just consider one very famous example of a consistent sphere truncation. So it was shown in 2015 by Baguet, Home, and Zampleben using modern techniques relying on exceptional field theory, that you can actually truncate type 2b supergravity on the phi sphere, and that it leads to a maximally supersymmetric supergravity theory in 5 dimensions, which has an SO6 gauge symmetric group. So 15 vector fields and a lot of scalars which are charged under this SO6 symmetry. So why is this an important tool? It means that, okay, it's hard to construct these sphere truncations, but if you have them, by definition, it allows you to uplift any solution of the lower dimensional theory to a solution of the higher dimensional theory. So if you scan the scalar potential of this lower dimensional theory and you find a critical point, then with your truncation ansatz, you can immediately uplift it to a solution of type 2b supergravity. If you find a different solution, well, you also be able to uplift it. Of course, the internal space will have a different geometry, but the topology will be the same. Okay, in particular, in this theory, there is a critical point at the center of the moduli space, which is an ADS5 solution, and it uplifts on the round sphere to ADS5 cross S5, which is the near-horizon geometry of this brane. The second reason why these truncations are very powerful is because if you're interested in the dual field theory living on the boundary of the ADS space, and you only want to learn certain things about the lowest BPS multiplet, then you can actually compute them holographically only using the lower dimensional theory. You don't need to do a full computation in higher dimension. Okay, so there is such a consistent truncation around the near-horizon geometry of the D3 brane, and it turns out actually that over the time people have constructed consistent truncation around the near-horizon geometry of all the DP branes until P is equal to 0. So the natural question is to ask, okay, there's really a lot of text missing here. Okay, but the equation is here. So the natural question is to ask whether you can actually build a consistent truncation around the near-horizon geometry of the D-1 brane. And okay, to remind you, so the D-1 brane is a half supersymmetric solution of Euclidean type 2b supergravity. And it takes the following form. So the weird thing now is that the metric, I wrote it at ADS1 cross S9 earlier, but this is too naive. The metric in the Einstein frame is just flat Euclidean space. And here I wrote it in spherical coordinates. So this t here, which is some kind of Euclidean time, is really just a radius. And it has also a dilaton and an action which are turned on, which is equal to some harmonic function, depending on the charge of the d-1 brane, which is related to n, the number of d brane. So this is the background for the d-1 brane, and so it was conjectured to be the holographic dual of the IKKT matrix model, and now the holographic coordinate is this radius or Euclidean time coordinate t. The question I ask now is whether it's possible to build a consistent truncation around this 9 sphere that you have here. And while there is absolutely no reason to expect based on symmetry argument that it exists, well, we still were able to construct it. So, I mean, this is the slide that essentially shows it. So the starting point is we take a subsector of Euclidean type 2b supergravity where you only have well, this is the Lagrangian, you just have the Ricci scalar, and then you have the dilaton and the axion. The fact that you have now switched to Euclidean signature flips the sign of the axion kinetic term, and this is what allows to a flat space solution, because the, the energy momentum tensor between the axion and the dilaton can actually vanish. And so the claim now is that if you do this truncation ansatz, where on the left-hand side you see the 10-dimensional fields, and on the right-hand side you see the fields of a one-dimensional theory, which is this one, where all the fields here only depend on this time coordinate t. And this mu here are the embedding coordinates of the sphere. So if you plug this truncation ansatz into the field equation of the theory, you will find actually the field equations of this lower dimensional theory. So let me describe a tiny bit what we have here. So the modes that you keep here are actually just scalar fields and some SO10 gauge fields. So you have a dilaton phi here, the dot is a derivative with respect to time. You have scalars that I call here Tij, which is a unimodular matrix. The scalars actually parameterize the coset space, which is a cell 10 over SO10. So this is the kinetic term for these scalar fields. And this is the scalar potential for the scalar fields, which depend on the dilaton and this Ti and the scalars packaged inside the matrices Tij, which are symmetric and unimodular. And you also have an Einbein E. So of course here, I mean, it's a bit naive to precise this, but there are no curvature tensor. You're in one dimension, so that's why you don't see any Ricci scalar. That's also why you don't see any curvature for the SO10 gauge fields. So the only place where they appear are inside these covariant derivatives dt here. Yeah. So the variation with respect to this Einbein and these gauges, they actually just lead to first order constraint on this system. So you can call it supergravity in the sense that, I mean, describes fluctuations, the lowest fluctuations of a gravitational theory in 10 dimensions. But if you look at it just from the point of view of one dimension, it's more, I mean, some SO10 gauge quantum mechanics. Okay. So yeah, the details, I mean, of course, are not so important of these big formulas. Now, the question is, you can say, okay, you have a consistent truncation, so you can look for solutions of this theory. The first thing you can look for is a solution which would preserve the SO10 invariance of the theory. So the only thing you can write down is actually the solution where this matrix Tij is just the identity. You set all the scalar fields to 0. And if you actually, I mean, and the Einbein takes a certain form, the dilaton as well, and if you plug this solution inside this truncation ansatz, you can uplift it to a solution in 10 dimensions, and what you find exactly is this solution again. So it contains the Nereiden geometry of the d-1 brane. Okay, so of course that's not the full story. I mean, in practice you would like to say that you have a consistent truncation of the full type 2b theory, which also includes the p-forms and so on, but I mean, the truncation ansatz, although I think it will exist, will look extremely complicated. So instead of this, to really connect with the IKKT model, what we've decided to do is to actually directly supersymmetrize in one dimension. So let me say a few words about this. Again, the details are not so important, but the few points that you should take away is that if you want to ask for maximal supersymmetry in one dimension, you have to kind of enlarge your field's content. So in the scalar sector, on top of this Einbein, dilaton, the gauge fields, and the scalar fields that were in Tij, you have 120 more scalar fields that are axionic scalar fields. And then, of course, you have all the fermions. So here, of course, you're in one dimension, so they don't really have any Lorentz structure, but they do transform under the SO10 symmetry of the theory, and they transform a 32-component spinor on the SO10. So you have a gravitini, which has 32 components, some spin 1/2, which I call lambda, which has also 32 components. You have a vector spinor, which I call Ka. And essentially, if you turn the crank, well, you can actually derive the full maximally supersymmetric completion of this one-dimensional theory. The first terms in blue here, they were already present on the previous slide. This is now a kinetic term from these additional axionic scalar fields, the 120 additional scalar fields. You have a scalar potential, which is quite complicated. It contains the terms you saw on the previous slide, but now it also contains many other terms with the additional axionic scalar fields. It goes up to axions to the 10. You have a topological term which is quartic in this axionic scalar fields, and then you have all the fermionic terms, and you can notice here that you don't have any kinetic term for the gravitino because the Arieta-Schwinger term in one dimension naturally vanishes. Okay, very good. So of course, if I give you a supersymmetric Lagrangian, I should also give you the supersymmetry transformation, but there is no need to really dive into details here. But essentially, I just give you like the variations of the fermionic fields in the sector where these axionic fields Aijk is equal to 0. And what you see is that they take a rather simple form. And they involve this chirality, this SO10 chirality matrix gamma star. And what you can do is use them to find actually supersymmetric solution of this one-dimensional theory on top of the one that I already presented by finding configurations, bosonic configurations, which satisfies delta epsilon, variation of the supersymmetry variation of the fermion is equal to 0. Because in all this variation, one term carries the chirality matrix and the other one doesn't. What you can see very quickly here is that essentially you have only two possibilities. You can either have non-supersymmetric configurations or you can have half supersymmetric configurations. And in order to have these half supersymmetric configurations, the only possibility is that these variations have to recombine such that you get projectors on this supersymmetry parameter. And such that you're actually able to find, a killing spinor with only half of the components. And so in order to have these projectors that appear here, this imposes certain first-order equations on the bosonic fields. And you can check that these first-order equations on the bosonic fields, they actually imply all the field equations in the theory. And you can solve them also exactly. So this means that in this sector, where this axionic field Aijk is equal to 0, you're able to find the most general half supersymmetric solution of the theory. It takes the following form. So essentially, without loss of generality, you can write this Tij metric as being diagonal with some element on its diagonal, which are given by the following function in terms of the time t. So these Ci's are real constants that specify the solution. So you see that for Ci's that are not equal to each other, this solution typically break the SO10 symmetry. If you take all the Ci's to be equal, you recover the D-1 brane solution that I presented before. So this solution, when you actually break SO10, we expect them to correspond in the matrix model we expect them to be dual to states that are in the Coulomb branch of the matrix model. We'll start turning on certain VEV for some of the operators that I will present before. So I wanted to say maybe one or two more words about this solution, but I'm not sure I have time. So I'll just say that in the bulk, what they correspond to, when you uplift them, what you find is that actually the 10-dimensional metric is always flat, and it corresponds to actually taking the instanton, which were at t is equal to 0 before, and just smearing them in the 10-dimensional space in a way that preserve the symmetry that, like SOP times SOQ, so the things I wanted to say here. So this is in some sense very analogous to the smear disrebrane of Friedman, Gupser, Pilch, and Warner for n equal 4 super Young mass. Maybe one last thing, not to say too much thing on this slide, but these solutions, you can actually uplift them even further to some solutions of pure Lorentzian gravity in 12 dimensions, and they actually correspond to PP wave solution. This follows the work of Zeitlin in 97. Okay, so finally, in the last few minutes, let me come back to the matrix model. So this is the action I presented in the beginning. So X and psi were the bosonic and fermionic matrices. So you have 16 supercharges, because this time the spinner satisfies this chiarity condition, the supersymmetry parameter. And the algebra here, because you're in 0 dimension, there is no translation on the right-hand side of a commutator of 2 supersymmetry variation. It's just equal to an SUN rotation. Yeah. So the operators I'm interested in are the single trace operators. So the ones that take the following form with any number of X of bosonic and fermionic matrices inside the trace. And so the operators, those operators, if you factorize out the field equation of the theory, they arise into certain supermultiplets. And among these supermultiplets, you either have long or short multiplets. The short multiplets, which are also known as BPS multiplets, they arrange into a tower, which I call Bn. And for each of these multiplets, for each n, it combines the following SO10 representation for the states. So it's always based on the lowest weight state, which corresponds to an operator where you take the trace of n bosonic matrices and you symmetrize and remove the trace. So if you look at the lowest one for n is equal to 2, what you find is the following representations for the operators that are inside of here. So 54 plus 144 and 120. The first one and the last one are bosonic operators. The last one is a fermionic one. And so the dictionary we proposed, these are the operators written in terms of the X and psi matrices. So as I said, this is bosonic operator, fermionic and bosonic one. And so the dictionary that is purely based on kinematics at this point is between this lowest multiplex of BPS operators and the fields that appear in this one-dimensional supergravity, which I've shown you a few slides ago. So these are the scalar fields. This is this vector spinner that I showed you, and these are the axionic fields, 120 of them. And finally, yeah, you can also see, you can compute actually the supersymmetry variation of this multiplet of BPS operator. This is what you'll find. So there is some kind of important structure. So if you apply 2 supersymmetry transformation, you find 0. And this is due to the fact that since you don't have any translation in 0 dimension, I mean, this nilpotent structure emerges. And you can also see from here then that if you, for instance, turn on a VEV for this first operator, the one in the 54, theta AB, of course, you don't break any supersymmetry because it never appears on the right-hand side of the supersymmetry variations. Okay, so maybe I'll just give some future directions and then I'll stop. With this setup that we have now, of course, what would be nice to do is to have some clear computation of holographic correlators using the SO10 one-dimensional supergravity we constructed and to compare to certain correlation functions in IKT matrix model. So this will require using the framework of holographic renormalization. But I should say here just that, I mean, this will be subtle, interesting but subtle, because these correlation functions that you're computing are really just numbers here, since you're in 0 dimension. So the normalization of this correlation function will be a subtle point. The other thing we could do is generalize this one-dimensional supergravity to SOPQ gauging, where P plus Q is equal to 10, so this should be quite easy to do. And these are usually expected to arise from Kaluza-Klein truncations on hyperboloids, starting from 10 dimensions. Another direction would be to look at truncation of this type 2b star supergravities in 10 dimensions of Chris Hull. I think this could have some importance if you want to actually now look at holography for the Lorentzian version of the IKKT model. And then finally, no, not finally, one of the things also you can do is look for other solutions in the SO10 gauge supergravity, and ones which involves axionic fields which do not vanish, and typically those are ones which are dual to mass deformations of the matrix model. So it'd be interesting to see whether we would be able to find a solution perhaps that is related to the mass deformation as polarized, that is known as polarized IKKT, or the solutions that are known as spherical branes. And then finally, but this is extremely speculative, but okay, I mean, it's a bit of a wishful thinking. I think this one-dimensional supergravity seems like an appropriate framework to use supersymmetric localization and obtain perhaps certain exact reasons. And I'd be very curious to do a one-loop determinant computation using this one-dimensional theory and to see whether it reproduces maybe certain features of the results of Moore, Nekrasov, and Chatashvili, which have applied supersymmetric localization for IKKT and derived the partition function exactly. Thank you very much. Yeah.
So it looks like that small a's are responsible for these three-form fluxes in 10 dimensions. But is there any operator or these fields in one dimension that corresponds to the 5-form?
Sorry, the small a's, now they are fields actually in one dimension. These fields here.
Yeah.
Yeah.
It feels like they are sort of these modes of the 10-dimensional 3-form.
Yeah, so actually, yeah, because the full truncation that is very nonlinear, they will actually spread in all of the fields in 10 dimension when you turn them on. So for sure, if you turn them off, you will not get any higher form in 10 dimension. They are the only contribution to this higher, to the, for instance, the NSNS and RR 2 forms and the 4 form. Their truncation and that will definitely involve the scalar fields. So if you actually have solutions that have the scalar field set to 0, you will never uplift them to solutions where you have like RR and NSNS 2 forms turned on.
Right. So is it correct to say that they are sort of the one-dimensional analogs of these 3 forms? And I think I'm just still a bit confused. Are they the one-dimensional analogs of the 10-dimensional 3 forms? So if you take the 10-dimensional
well, I wouldn't say they are analogs, but for sure they will.
They come from those.
They will originate from those, yes. But
right. Is there anything that originates from the 5 forms? For example,
yeah, they will
have all these matchings of operators with these modes, and there are these ones with commutators with 3 matrices, looks like the 3 form, but are there ones with 5 forms that?
Yeah, you can't draw such a direct dictionary. I mean, in order to have a solution with also a 4 form turned on, or the self-dual 4 form, for sure you will need a solution that also turns on this 120 scalars in 1 dimension. But yeah, the relation is very nonlinear. But yeah.
Thanks, Franz, for the interesting talk. In the next slide, where you present the where you present the solution, maybe it was the previous one.
This one?
No, where you find the solution of the you're showing it. It's called sphere truncation or something like that. Yeah, yeah. This. What is the regime in which I should trust this solution in particular? What is the behavior of the string coupling as a function of this one dimension?
Well, so that's actually a very subtle point because here, I mean, so usually when you do this holography for DP branes where P is not -1, so you can trust the supergravity solution to do holography only in a certain range of the holographic radius because you can interpret it as some energy. And so it shouldn't be too big because otherwise the space would be too curved, or it should be too small, otherwise the dilaton would blow up. The problem is here that the near horizon geometry of this D-1 brane solution is actually flat.
And what about the asymptotics?
Sorry?
What about the asymptotic region?
The asymptotic is just flat space.
So you have flat space both in the asymptotic and the near horizon, is that what you said?
Yeah, yeah. So in the Einstein frame, this is completely flat. In the string frame, it becomes a wormhole which connects two asymptotic flick-like regions. But once you take the near horizon geometry, the near horizon is flat. Yeah.
Thanks.
So what is, I just missed, why you consider New Horizon limit at all? Your construction works for any.
Sorry?
Why you're considering New Horizon limit here? So your construction works in general, right?
I'm not saying, in this case, I'm not saying that taking the New Horizon limit is necessary. It's a,
okay, but you change supersymmetry, so that presumably changes, is that the case or not?
I change supersymmetry?
When you take New Horizon limit, in other examples, we know that supersymmetry is enhanced.
Well,
it doesn't happen. I don't remember. I don't know.
No, so here I'm completely blind to this. I mean,
but you use supersymmetry to classify your whatever states. Comparing your IKKT model has maximal supersymmetry as far as CFT. Well, not CFT. As long as this zero-dimensional theory is concerned, it's just reduction of unequal form.
Yeah.
So it should be matching to whatever supersymmetry you have in your supergraph.
Yeah. So
it should be important that you actually drop one in the dilaton, but I don't quite get where.
So in fact, the only thing you capture in the consistent congregation is really the solution where you drop the one.
Oh, it's only that one.
It's only this one that you reproduce.
Okay.
Yeah.
Second question: what happens if you repeat the same for D0 brane?
Yeah. So that actually, I've worked on that as well in some other people. In this case, yeah, there's a slide I skipped, but I'm not sure there is any text on it. Yeah, there is. It's this one. I wanted to mention it. There is a similar story where things are a bit more under control because this time the New Horizon geometry is not just flat space, but it's really some ADS2 cross S8, which is warped by dilaton because so what happens is that you have a consistent truncation of 2A supergravity on S8 to a theory in 2 dimensions, which is known as SO9 gauge supergravity. And there at the center of the moduli space, you have a solution which is not an ADS point, but a domain wall, so ADS with a non-constant dilaton. And if you uplift it, it's the same story. You get the New Horizon geometry of the D0 brane, which is this warped ADS2 cross S8. And there actually people used the lower dimensional theory to compute certain 2-point and 3-point functions and match certain correlators in the BFSS matrix model, which is the dual. Yeah.
So I don't find any coupling constant in your theory, either matrix side or in the gravity side. So it looks like it's a comparing free theory with free theory. Is it true?
Yeah. Yeah. This issue of the coupling constant in IKKT is a bit subtle because, as you see, you don't have a kinetic term in the action. So, I mean, you're free to just redefine your matrices to absorb what you call G-Young bits. So, how to make sense of the coupling constant in IKKT is a bit unclear to me. The only thing I can say is that what I'm talking about is that very large N. But at the same time, the original conjecture of the IKKT is that at large N, you should be really describing free type 2B string in flat space. And in a way, from the point of view of supergravity, it's a little bit what you're seeing. I mean, you're seeing essentially type 2B supergravity on flat space. The question is how to make this more precise. So the only things I've been saying so far here are just purely relying on like matching representations. And I'm not making any statement about the regime or the dynamics or anything.
No more question. We can thank the speaker again. Thanks for the morning section and good afternoon.
Oh yeah, we are giving you.